the company didn't do everything in time, therefore it was the main reason that the bus departed with delay, and then due to traffic jam it was finally great delay. We discussed it with company and told that such behavior it's impossible, and I hope that in future we shall change this company, we shall hire another company, surely. And today I hope everything was perfect. But in any case, please apologize us for this. Thank you very much. Now we can listen to our first lecture for today.
So good morning, everybody. I'm Italo Capuzzo-Locetta. I'm supposed to be the chairman of this first part of this morning session, and my pleasure is to introduce Manuel Del Pino from Universidad de Chile. He will talk on variation on the Bombieri de Giorgi Giusti minimal graph. Please, Manuel.
Thank you very much. Well, I would like, first of all, to express my gratitude for the invitation. It's a great opportunity to come here. Also, well, it's a sad occasion, but about to learn about the disease of Professor Pohosaev. So I would like to dedicate this talk also in his honor. So, well, what I would like to speak today is, well, it's essentially a line of problems we have been doing in the last few years. This is, in good part, in most parties, collaboration with Junchen Wei and other collaborators, and it is related with the so-called Bombieri de Giorgi Giusti minimal graph that I will explain in a moment what it is. Okay, so I start with the classical minimal surface equation, which is the one up there, which arises as the first variation of the area functional, this, okay? So if we the first variation of this functional, the formal first variation of this functional equal to 0 amounts to solving this equation. So this is the so-called minimal surface equation. And there is a classical question in the theory of minimal surfaces, which is actually a Liouville theorem. It's a Liouville theorem for the minimal surface for the minimal surface equation, which is this quasi-linear elliptic PD, and this is called the Bernstein's problem. And while this is what and the question in this Liouville theorem is whether solutions of these entire solutions of this elliptic problem are all trivial. Okay, what are the trivial solutions? Trivial solutions are linear functions. Because the gradient of this will be a constant, right? So divergence is 0. So these are trivial solutions. And the question is whether or not there are other solutions that are not necessarily linear functions. This is entire solutions that are not linear functions. In other words, saying in geometric terms, the graph of f is in Rn is a minimal surface if it satisfies this equation, and the question is whether an entire minimal graph in Rn is necessarily a hyperplane. This is Bernstein's question. Now, what is it known? Bernstein actually proved this fact about 1910. Prove it for n equals 3, so for actual two-dimensional surfaces. Two-dimensional graph, okay, in R3 entire must be a hyperplane. in dimension 2. This was originally proven more than 100 years ago by Bernstein himself. There were other proofs. If I'm not wrong, there was a proof by Nietzsche about 1957, and there is a proof and a conjecture known as Bernstein's problem. Actually, was raised by and symmetric with respect to the line U equal V. Okay, so this is the example of von Biere de Giorgi Giusti, which is, by the way, the construction of the super solution in particular is quite sophisticated. Huh? It's not a simple thing. What I would like to show you is some questions that in the literature of elliptic PDEs that are connected with Bernstein's problem, and for which the von Biere de Giorgi Giusti minimal graph is a tool to find interesting examples. Okay, so let me begin with an equation that is very classical, which is the one up there, the Allen-Kahn equation. I will put it here for reference. Plus, I will write it this way. Okay, and this equation I'll call from now on AC. Okay. So this is a variational problem whose origins are in the gradient theory phase transitions. It's the simplest model of this type in which you can imagine that you have, I don't know, some material with two states, solid and liquid, say, okay, which correspond to the states +1 and -1, which are actually global minimizers in any sense, in any reasonable sense to this functional. Okay, and the interesting thing is to find configurations or critical points or local minimizers or whatever where the two states coexist, say where U is most of the time close to 1 and close to -1, but with the region separated by a transition, okay, a transition region, a wall, where the solution goes to -1 to +1, which is known as the interface. It's usually known as the interface. So the interesting solution for us, or for the Allen-Kahn equation, are those of this type, that are actually have a transition from the value -1 in certain region of the space towards it's a complementary region where it has the other value. Okay, so these are the interesting solutions for us, where the two phases plus and -1 coexist. Okay. Of course, the solution is not a discontinuous function. It has a transition, sharp transition between plus and -1. Okay, well, of course, the first thing to consider is the one-dimensional case. In the one-dimensional case, the Allen-Kahn equation has explicit solution doing what I said. If I can make a little drawing. Okay, so this is what I call T. 1 -1, and this guy I will call W from now on. This is hyperbolic tangent of T over square root of 2. And this is the unique solution, except for translations in space in T, with this property that connect the values -1 and +1. Say, what is special about this nonlinearity? What is special about this nonlinearity, U times U minus U squared, is that this is minus W prime of U, where W is a double well potential. Yeah? It's a double well potential with wells of the same height. Say two global minimizers that are non-degenerate. Yeah? This is in general, everything I speak here is also valid for a nonlinearity that has this qualitative feature. Yeah? Two global minimizers with the same height, the Allen-Kahn equation. They are non-degenerate, unlike in the talk of Professor Ilyasov in the other day, which he considered the degenerate case. Okay, now, of course, if you have a solution in 1D, the one-dimensional solution inherits automatically solutions in any dimension, right? I mean, you can simply evaluate the one-dimensional solution in one of the variables, right? And you have a solution in entire space. Say more in general, how to pose that issue is to say that any solution of the form W evaluated that Z, where Z is x minus p dot nu, where nu is some unit vector and p just anything, is going to be a solution of the Alenkane equation, the AC equation, this one, in Rn. Okay, so there is a question actually raised, very, very interesting question, raised by Ennio De Giorgi in 1978 concerning the Alenkane equation. And actually what is appealing, what was especially appealing of this question, is that it established a connection between Bernstein's problem and you know, the theory of semilinear elliptic PDEs, and in particular, or this theory of phase transitions. And the question of De Giorgi was like this. Actually, well, this is a conjecture. The conjecture is the following: assume that we have an entire solution, just like parallel would be an entire minimal graph of this semilinear elliptic PDE in Rn. Yeah. And we assume that this solution is monotone in one direction. Say that the partial derivative of u along the nth direction, and could be just anything, right, is positive. Then, and this is the literal his literal statement, at least when dimension n is less than or equal to 8, then u of x has this form. So it's one of the trivial solutions that I described in the previous slide. Yeah, say simply the one-dimensional solution evaluated as the linear variable. What is usually said in a situation like this is that the solution has one-dimensional symmetry, 1D symmetry. Yeah. Now, the statement, the way actually he presented the statement, which is equivalent, yeah, is this: is that at least when n is less than or equal than 8, all level sets of u, all these sets, u equal lambda, must be hyperplanes. Must be hyperplanes. The monotonicity will say that they are parallel. Okay, so and therefore the solution depends only on the normal coordinate, the common normal coordinate to those hyperplanes. Okay, so this is the Giorgi conjecture. And concerning the Giorgi conjecture for the Alenkane equation, there has been many works in the literature over the years. I will just mention very few that have maybe very definite answers, but these are not by no means the only ones. There are many in the course of the years. And the first definite answer for the case of 2D, just two space dimensions, was given by Gusub and Gui in a paper in 1998. They proved that the result was true. Actually, it was this was in parallel connected to another paper by Stig, Caffarelli, Nirenberg. Okay, they used a very nice trick. Okay, and it's a very simple proof, but very, very cute. But that relied on dimension in the use of certain estimate of the solution in large balls. What happens is that it was not easy to prove that estimate hold, but they proved the corresponding, the necessary estimate was proven by Ambrosio and Cabré in dimension 3, and they actually proved the result in 2000. Okay, so, and as I mentioned, after many partial contributions in between or with related problems and so on, there was this answer, this very satisfactory answer, however not complete, by Ovidio Sabin between dimensions 4 and 8. The paper was published in 2009, And the thing was this. He proved that if in addition of the assumption of de Giorgi, namely the monotonicity in one direction, if in addition to that, we know that the limits along xn for you, which exists, of course, because it's monotone in the direction xn and bounded, if those limits happen to be respectively +1 in one direction, -1 in the other, and for all x prime, then the result of the Giorgi statement is true. Okay, so and this is not just a minor technical assumption, because it implies the local minimizing character of the solution, as this was established by other people before, Ambrosio, Alberti, Cabré, and of course this is a little subtle, but very important, okay, is that this assumption doesn't include uniformity. This limit is not uniform in x prime, by no means. In fact, the statement that when the limits are plus and minus 1 uniformly in x prime, it turns out that that implies the one-dimensional symmetry, namely the dependency in xn only, in this case, without any monotonicity assumption or requirement in dimension. This was called Gibbon's conjecture, and there were, well, several groups that proved this in early 2000s. Yeah, but that's a different thing. Here, the limit is not uniform. No? Okay, so the full question is open so far, but this is perhaps the most satisfactory answer. There is a new proof by Kelly Wang that is now in archive. Okay, so how did de Giorgi figure out the connection between the Alencane equation and the theory of minimal surfaces? Okay, the reason is that in a little earlier, in 1977, Modica and Mortola published a very famous result, okay, that originated the so-called theory of gamma convergence. Yeah, the variational, I mean, basis of many developments over the last decades in the calculus of variations. Yeah, Modica and Mortola established in 1977 the following. Okay, what they proved is that if you have a solution, a sequence of solutions to this equation, not in Rn, you put an epsilon in front of the Laplacian, so it's slightly different. We put an epsilon. So if you have a sequence of solutions to this, where the index is epsilon, okay, in a bounded domain, which in addition are local minimizers of the energy I wrote before. So, okay, the minimizers of the associated energy, local minimizers, and a suitable bound holds for it, for the energies, then these solutions must approach a function that is +1 somewhere, -1 in the complement, and with an interface which is in some generalized sense a minimal surface. Okay, so this is the result by Modica and Mortola, and this is how the connection with the Alencane equation comes, because okay, so the equation without epsilon, you can introduce the epsilon simply by scaling. You are still in entire, an entire solution. So, well, the level sets of this, what the statement of de Giorgi is that the level sets of this for epsilon small or epsilon large doesn't matter, as long as the U is monotone in one direction, will be more or less like the limiting minimal surface, and the limiting minimal surface is a graph of functions of the complementary variables of xn. And then, well, what he said, or what he correctly stated, was that it should behave like the minimal graphs, the minimal graphs. Okay, so this is the connection with minimal surfaces, and but what we will take, or what I consider here, what we consider actually is somehow the opposite view of that of Modica and Mortola, in which they take, okay, a sequence of critical points, and then they see what happens in the limit. Okay, and we take a little bit the opposite way, in the sense that actually we start with the limiting interface, and what we are interested is in building up a solution, okay, that has a transition layer near the surface gamma, yeah, the minimal surface gamma. Okay, so given an embedded minimal surface in Rn that splits the complement of say, gamma splits Rn into two components, yeah, then what we want to find is a solution U epsilon such that in the complement of gamma, say in these two components, omega plus minus, the solution goes respectively to +1 and -1 as epsilon goes to 0. And of course, then therefore has a transition layer up near, okay, this gamma. This is what we want to construct. So it's a little bit opposite. We don't start with a family of solutions and then characterize what happens at the limit, but rather we start at the limit and we try to construct a solution with the limiting feature, okay? And then we consider this problem for for gamma, the Bombieri-Giorgi-Giusti graph in R9. And we find then this result a few years ago, 3 years ago, that says that if you start with the Bombieri-Giorgi-Giusti minimal graph, okay, then you can find a solution to the equation with the epsilon in front. No, without epsilon in front, just this equation. Yes. No, this is for AC epsilon. This is with the epsilon in front. So you can find a bounded solution of the AC epsilon, which is monotone in the x9 direction, and that has the form, this guy, the transition, the one-dimensional transition layer, evaluated at the normal direction of gamma. Okay, since gamma is not a hyperplane, level sets of this function are not going to be hyperplanes in particular. However, we do have monotonicity in one direction, and in fact, we can also check that this holds true, which is rather natural. And this solution, this family of solutions, yeah, that has transition layer near gamma, near the Bombieri-Giorgi-Giusti graph, turns out to be, it's not the right word, a counterexample, because obviously the Giorgi, when he said, well, this should be true up to dimension 8, he certainly thought, well, in dimension 9, perhaps something could go wrong. And in fact, that's the case. This is what we proved, and this is a question that was, I would say, there were two parallel lines, people trying to prove that and people trying to prove the direct side in the course of the years. So this is our result, together with Mike Kowalczyk from University of Chile and Jun Chen Wei. So let me give you just very, very brief intuition of how this goes, or how, rather than the construction, say some heuristic argument that tells why things work, why we can construct such an example. Well, there is, first of all, this well-known expression for the Laplacian in local coordinates associated to gamma. Let's consider a tubular neighborhood of the surface gamma. Okay, z is the normal coordinate, so all points can be written in this way: a point in gamma plus some scalar z times the normal for a choice of the normal coordinate, and well, the Laplacian can be written in this way. So this is Laplace-Beltrami operator of this manifold. Y is the coordinate of the manifold, z is a parameter. And this is the mean curvature, and this is derivative in the z direction. So this is a well-known formula for the Laplacian, which is good because for us, because we want to evaluate it at first approximations of a solution that depend on z, essentially, only. And, and by the way, this guy can be written explicitly in terms of the principal curvatures of gamma itself. If kappa i's are the principal curvatures, the eigenvalues of the second fundamental form for the surface gamma, then this mean curvature of gamma z can be explicitly written this way. This is very important for us. Well, okay, so what do I want to find? What I want to find is a solution to this problem with the epsilon. With epsilon or with no epsilon, by the way, I insist, it's the same. You simply pass from one to the other by scaling. We are considering entire solutions. So if I express this equation in the terms of the new coordinates, well, coordinates y in gamma and z, yeah? This is not gamma epsilon, this is gamma. Then you end up with this expression, of course. And here is one key point. This is the key. The key of the argument is actually consider a first approximation. Okay, the method is the following: is to construct a good first approximation, then linearize around it, and then use some type of fixed point argument in order to solve for an actual solution. So the solution we consider has the form this W, the hyperbolic tangent, evaluated at z over epsilon, where z is the normal coordinate, and then we add a translation in the argument, which is a function of y only. Y is the function on gamma, on the minimal surface. So this is the ansatz. This is the ansatz, and here h is a parameter. The function h is a parameter. So essentially what we don't know exactly what this function h determines is the zero level set or of this U0. Okay, so now how do we find this h? Or well, first of all, if we evaluate the error of approximation when we evaluate at w of this variable, then you obtain this expression up here. And this is a key point, okay, is to expand the curvature of gamma z in the following way. Yeah? If you do this, then at the end, okay, at the end of the day, you end up with this expression for the error. A cubic of epsilon times this operator, this elliptic operator on h, yeah, times w prime, plus the sum of the curvatures cubed times the square w prime, and then there is this quadratic term in epsilon, but times tw prime, and then there are lower order terms, say terms that are, say, smaller. This is our actual setting. And then, well, the equation we want to solve is this, S of U0 plus some small remainder, and that gives us an equation for phi, which is the one up here, yeah, this linear equation. And if you formally make expansion in powers of epsilon for, with coefficients depending on t and y, for, say, for formal power series expansion in the nonlinear equation, then you end up with very simple equations for these terms phi2 and phi3. The term phi2 solves an equation like this, because we let formally epsilon go to 0, so the dependence in epsilon disappeared. And we have this equation only, which is equation for a function of t. Y here is a parameter. But you can solve this equation when? For a bounded phi2. Well, when this guy is orthogonal to the kernel of this operator, to the bounded kernel of this operator. So this is just ODE theory, just formula of variation of parameters or Fredholm alternative, okay? And for phi3, you have this guy. What happens is that the first guy, okay, this guy is always, if you have an equation like this, if this equation will be solvable in L infinity, if and only if this orthogonality condition holds. But this equation up here, that condition for this guy is automatic, okay? Because tw prime is an odd function. It's an odd function you multiply by w prime. It's an odd sorry, it's even. Okay. I mean, tw prime is odd and w prime is even, so the integral is 0 when you test against w prime. Okay. However, the second thing is not automatic, and amounts to choosing an h. And then this equation up here determines h. This is the orthogonality relation. So the equation we have to solve is this operator, which is the Jacobi operator of the minimal surface gamma, equal to the sum of the curvatures cubed. And, well, let me say that luckily enough, we can solve this problem. It's not easy to solve it for many technical reasons. That's not the case to give detail. But the main thing is that since we have the expansion of the surface at infinity with separation of variables, then we can compute this term very accurately. Yeah? In fact, it separates variables itself. Yeah? It has this form, some function of theta divided by r cubed. And then essentially we can approximate the solution, a solution to this linear equation by something that separates variables itself. Okay? And after doing that, well, we insist in iterations and barrier arguments and so on, and we can solve it. Of course, the problem we need to solve is a nonlinear one at the end. For the actual proof, we reduce the whole problem to solve an equation which is a nonlinear perturbation of this. Nonlinear, non-local perturbation in H, I mean. And we develop like a theory that allows us to make fixed point. Okay? Okay, so of course we can do this for other minimal surfaces. Why not? Okay, and one example that we consider is the case of finite Morse index solutions, minimal surfaces with finite Morse index solutions. Those are there is quite developed theory for these objects, complete embedded minimal surfaces with finite total curvature, Gauss curvature. And in fact, for such objects, we can find a solution with the same feature, say with the transition layer around the surface for the equation AC epsilon, and whose Morse index coincides with the index of gamma. That's not easy to prove, but it's true. Okay, and but as long as there is a technical condition satisfied in addition, which is non-degeneracy. Non-degeneracy, which amounts to the fact that the kernel, the Jacobi fields only arise from, how do you say, from rigid motions of the surface. Okay, so this is the situation. Of course, let's say rather than the technical thing, it's nice to know this because it's easier to explain. But for instance, if you have a catenoid, you can find an axially symmetric solution of the equation, of the Lenkan equation, where the zero level set will look like a catenoid. Will look like a catenoid. All level sets actually are sort of are very close to a sort of a foliation by catenoids, if you may say something like that. Okay, so this is the main example. Perhaps this has Morse index 1. It's a mountain path. Okay, a lot has been done anyway concerning this type of solutions by Jun Cheng and collaborators. And you can also consider the Costa-Hoffman mixed surface, which is a very famous example, actually, of surface with total mean curvature, finite total mean curvature in the 80s, and extended by Hoffman and Mix, and for which you have higher Morse index. Yeah, and well, anyway, you can also consider, of course, the close relative of the catenoid, which is the helicoid, right? Sort of its conjugate. This case is actually simpler. It's much simpler. In fact, in a work together with Monica Musso, who's here, Frank Paccard, we proved this is not an asymptotic issue. That if you have a sufficiently dilated helicoid, then you can find a solution whose zero level set is exactly the helicoid. And otherwise, there is no such a solution. And this is what we proved a couple of years ago. So the threshold is exactly pi, actually, for this dilation constant. So here is not an asymptotic type topic. Okay, so this is what I was speaking was about variations, right, of the Bombiri de Giorgi Giusti minimal graph. Let me refer to a second variation, which is another classical problem in the semi-linear elliptic PD theory, okay, or literature, which is the overdetermined problem. The overdetermined problem is the following: is you consider a semi-linear elliptic equation of this form, say with F Lipschitz, okay? And the problem of finding positive solutions to this problem that are in addition bounded, why not? And that satisfy zero boundary condition and in addition a Neumann boundary condition. The Neumann boundary condition is constant, okay? The one who considered this problem first was Serrin, motivated in certain specific free boundary problems, yeah, in early 70s. So the question is this: what can we say about if? Of course, this is an overdetermined problem, so it's not clear that we can even solve it. And then the question is, well, if this problem is solvable, what constraints in the geometry of omega can we state? Can we find? Can we get? And Serrin in 1971 proved that omega is bounded, and there is a solution of this problem, of the Serrin's problem overdetermined. Then omega is necessarily a ball, and the solution is really symmetric. What he did was to adapt to this context Alexandrov reflection principle. Alexandrov, for his proof of the fact that the constant mean curvature surface compact was a ball, okay? Serrin adapted that to this setting and found the same result. And that originated what was called later the moving plane method by Giesecke-Nirenberg. Okay, so, but now the question is, well, what about if the domain is unbounded? And there are some answers for this. The question actually that I would like to refer to is the question for where this is an epigraph, my domain is an epigraph, unbounded domain which is an epigraph. Berestiki, Caffarelli, and Nirenberg in 1997, the paper is in CPAM, I forget to say, proved the following: proved that if this function phi is Lipschitz and asymptotically flat, say it goes to a constant at infinity, then the phi must be linear if there is a solution. And what that means is that the overdetermined problem is solvable. If the overdetermined problem is solvable, then there is the limit is, the domain has to be a half space. There has been some improvement in dimension, but and lowering of the conditions. But this question, which is a Bernstein type question, is far from being solved. In fact, it's probably much harder than the Giorgi conjecture itself, for instance. What we were able to find with Frank Packard and Junqing Wei was that in dimension 9 we can find an epigraph an entire epigraph where the problem is solvable. The overdetermined problem is solved. Okay, this is and as you can imagine, okay, the epigraph is a perturbation itself of that of the Bombieri de Giorgi Giusti solution. So this is what we find. The paper is in Archive. It's technically actually much more complicated than the one of the Giorgi, but it's along the same lines. Okay, just let me say that if you do the formal computations that I mentioned before, the condition you get in the limit is a little bit different. The condition is not that the curvature must be zero, minimal surface, which is what you find, but actually here you want that the mean curvature be constant. So that comes back to the, Serrin used the argument for the minimal surface, for the constant mean curvature surface. And it turns out more or less that now here the rule is this. If you have a constant mean curvature, a domain with a constant mean curvature boundary, then you can find, a solution of an overdetermined problem close to it, close to that domain, okay? For the domain close to it. This is the rule. We have done that for several examples. Besides, but anyway, I will not mention that. And the very last, just to conclude, the last variation that we consider, this is a joint work also with Totti Daskalopoulos from Columbia and Junqing Wei, Juan Davila from colleague of department, and Jun Cheng, which are translating solutions to the mean curvature flow, which is another problem of the quite very pretty problem. Say you have the evolution by mean curvature, is this equation, okay, this classical equation, and what we want to find are solutions that live at all times. Solutions that are sort of traveling waves. Actually, the interesting ones for us are these things. So are things that don't change shape and evolve along one direction with constant speed. So it's a traveling wave. They are traveling waves in some sense, okay? And the graphical self-translating solution, if this sigma is a graph of a function, are simply functions of this form, ct plus f of x. And the equation for f in that case is this one, is this variation of the minimal surface equation. And what we found was that what we are trying to solve is this question by Yuxia Wang in 2009, which is the following. Which is a variation of the Bernstein conjecture. Is it true that all entire solutions of this equation need to be convex? Well, if C is 0, it should be convex but also concave, so it should be a hyperplane. So this is an extension of the Bernstein problem, but for the traveling graphs, for mean curvature flow. This was proven actually to be true by Yuxia Wang in dimension 2. Solutions are in fact radial, right? And this is also connected with some, this is a self-translator that is mean convex but not convex, and that's an example that is actually appealing for people in this theory. If you could find it, okay? And let me tell you, just to make the story short, say Yuxia actually found examples in dimension 3 of convex non-radial solutions, but no example of non-convex things. And in fact, what we found is this. What we found is a solution of this equation that has this form. That is a function that at main order is a cube g of theta, and then there is a square times another function of theta plus a capital order of r. We're able to construct in dimension 8 again, or dimension 9 for the environment. We were able to find a solution to the Yuxia Wang problem. So this is the, you would say, the Bombieri-Giorgi-Giusti version for the traveling problem. Just to finish, I mentioned that we have been able to do, together with Juan Davila and Hien Nguyen, actually solutions that are kind of parallel with gluing methods, solutions that are parallel to this finite total mean curvature things. Solutions that will look like that, self-translator that will look like this, but where the wings here, the ends, become asymptotically paraboloids rather than planes or catenoids. They become paraboloids, parallel paraboloids. Yeah? And when I mean paraboloid, I mean a shape like this. Yeah? This is something we can construct. And we are now finishing the paper anyway. So thank you very much. This is...
Thank you very much also to Dina for your rich talk. And I'm asking if there are comments or questions. Seeger?
Your example for Alan Kane, where you showed there is some solution if epsilon tends to 0 tends to the minimal surface. It reminds me very much to the situation which is closer to harmonic maps, which was considered by Leon Simon. And there, if you somehow use the dynamical system approach, but there you would have to determine the, let me call it the stable manifold. Have you looked at that? You showed existence of a solution, but did you characterize those?
Your question is extremely interesting for me. In fact, it's something we want to do.
This is, this is a wrong situation because it's not a dynamical system of it's an elliptic one.
Finding something like a stable.
Yeah, but he he does in this case. He can characterize it. He also has to use a spectra to the linearization, what you also have, the Jacobi fields there. And I do not know when this was, but it's already a long time ago when he did that. He transformed, he was looking at singular...
For harmonic maps.
Because he had a solution in a singular point, like x over x absolute.
Yeah.
So singularity was just in one point, then he introduced radial coordinates in order to study that and wrote down this as a dynamical system with asymptotic behavior. You have the epsilon here. And I always was very much interested in that. Essentially, also the other question which you looked at, you essentially used the pendulum equation which you had for your G. It's very closely related to problems of just dynamical systems, but with the wrong situation. We are in the elliptic situation. Operators have the wrong sign.
That's right. No, absolutely. In fact, I think it is very interesting, and it is. I would say what we feel is our next step in various problems, in particular the harmonic map flow.
He has, in his case, he has a characterization.
Mm-hmm.
Because
of the full.
Yes, at least some approach, because you do not know how long they exist. Just you go out from a singular, you consider your harmonic, your minimal surface as a critical point of the dynamical system.
Yes, no, I understand. Thank you.
Thank you. Any more comments or questions? Please.
Could you please get back to the de Giorgi conjecture for the case of n between 4 and 8? I mean the additional 7 condition. Are any counterexamples known that if the condition is not satisfied, then the de Giorgi conjecture does not hold?
You mean the condition of these limits?
Exactly.
1?
Yes.
That as far as I know, there's no counterexample, or no, there is no statement like that. In the
Okay. Thank you.
Anyway, I think everybody believes that the limits must be plus and minus 1. That people have not been able to prove it. But
before you prove that it is not only a sufficient condition but is necessary as well, it's only sufficient.
Yeah, it is only sufficient.
Yes.
Not necessarily.
It's only sufficient. Yet, okay, thank you.
No, but it's an interesting question, in fact.
That is why I asked it.
Yeah.
Okay. So if there are no more questions, we thanks again Professor Del Pino. I guess we have 5 maybe 10 minutes more break before Ishi starts.
And this button is just the, my fingers are off. So, just, yeah. We use the blackboard, well, the whiteboard.
Probably, I don't think.
Okay, then I switch the light.
Oh, thank you.
second lecture this morning is by Professor Hitoshi Ishii from Waseda University in Tokyo. The title is Metastability. I'm sorry. Metastability for parabolic equation with drift. Please, Professor
Thank you
Ishii.
for introduction. So I would like to thank organizers for inviting me to this conference. Actually, because of this conference, I could meet Professor Pohojaev and Professor Ilin and Professor Anosov, sorry. Otherwise, I couldn't have a chance to see them. That was very great pleasure. Also, Professor Pohojaev, especially, he was very influential in Japan by his work on his inequality or identity. And so I also had chance to see him in Japan, maybe also in Waseda. And so last time I remember that I had some discussion with him in this conference. I'm sort of a person who is not so socialized enough, but he is very kind to be with me. So let me start my talk. And so this is joint work with my collaborator, Professor Sunganides of University of Chicago. And actually, last time also I gave a lecture, something joint work with him. So this is kind of continuation of joint work with Professor Sunganides. And so this is about parabolic differential equation with drift term. So this is my equation, and so this is a standard parabolic equation. So, but equation has a small parameter epsilon in front of second derivative of my second derivative of my unknown function u epsilon, and basically everything. So I have drift term given by function v, and diffusion coefficient is supposed to be, of course, non-negative definite matrix, and let me call square root of symmetric matrix A as sigma. So I can take just sigma to be, A to be sigma square, and sigma is non-negative definite. And I assume B and sigma are Lipschitz continuous function. And of course, this sign, symbol TR means trace, and dot means Euclidean inner product. And the question here is, of course, asymptotic behavior of function solution of U epsilon as epsilon and T goes to 0 and infinity. And actually, this is a report on what we did following what we learned from the work of Russian school on probability. And Friedrich Wenzel wrote a book some time ago, which is called, title is Random Perturbation of Dynamical System. I think this is a very popular book. And recently, Friedrich and Kolosov studied some kind of extension, what they did in the previous, Friedrich and Wenzel did in their book. And it is titled as Nonlinear Stochastic Perturbation of Dynamic Systems and Quasi-Linear Parabolic Equation. Actually, their result also investigate nonlinear problem, quasi-linear parabolic problem. But here, my study is not so advanced, so I have to concentrate to linear equation. Anyway, let me explain the assumption I do here. So I have a domain omega where my equation is posed, and domain omega contains origin. And this origin is a global asymptotically stable point of dynamical system given by OD x dot equal v of x. So this means that if you start, at least in the domain omega, with start means start, take the point as the initial data of this ordinary differential equation, then every solution goes to 0, origin, as t goes to infinity. So it is written here. And moreover, I assume that B has this property. So B direct inside to the domain omega. And so the flow look like this. So if you start outside omega, then it goes close to the boundary and will eventually go to 0 as t goes to infinity. This is a situation, basic assumption on my function B. And let me explain what Friedrich Wenzel did. And so let me assume that the sigma, so my diffusion coefficient is just 1. So my second order term of my parabolic equation is Laplacian U epsilon. And let consider this kind of stochastic differential equation. dx sub t epsilon equal b of x. So basically, ordinary differential equation x dot equal b of x is perturbed by Brownian motion multiplied by square root of 2 epsilon. So that corresponding PDE is just our equation. And let's consider the first exit time when the solution of this stochastic differential equation started from x, maybe inside omega, and when the first exit time from domain omega, which I call tau x sub x super epsilon. And they prove that this first exit time behave like e to the power m0 over epsilon, as epsilon goes to 0. Here, m0 is a positive constant, which I will describe more precisely. So if you don't have this term, so if you put epsilon to be 0, then by my assumption on function b, your solution of ODE do not exit from omega. The solution goes to 0 as t goes to infinity. So this should be, in some sense, when epsilon equals 0, this is plus infinity. Anyway, in some sense, it is same as the epsilon goes to 0, but because of this term, you have finite time where the solution of stochastic differential equation exit, and it is about very large but finite. And let me explain what is M0. M0 is given by by the solution of Hamilton-Jacob equation, which is in our case, in the present case, that means that A of x is identity matrix. My Hamiltonian is given by p squared plus b dot p. And then I consider this Hamilton-Jacob equation, and I assume solution to be 0 at the origin and consider the maximum solution of this equation, and you get a function which is positive except point 0. So maybe very simple example is when b of x equals minus x, and when omega is ball, then you can see that you can see that this function u of x, modulus of x squared over 2 satisfies this gradient of u equal x, and then this is minus x is my b, and then x squared minus x squared equals 0. So this is this function is solution of this Hamilton-Jacob equation, but indeed this is maximal solution under this restriction v of x equals 0. And Friedrich-Wenzel called this function so maximal subsolution or maximal just solution as quasi-potential. And actually in this special case, when v equal minus x, you have your equation can be written using this function v, since dv is function vector x. So if I have this formula. So this is potential form. I think because of this relation, Wenzel-Friedrich called this function v as quasi-potential. Anyway, constant m0 is given by this formula. So you take the you consider the function v, quasi-potential function v, and take the minimum over the boundary omega. And because I claim that this function is positive except origin, so, and this function v is Lipschitz function, and so this minimum value is positive. And then actually their claim is more than that, and they say that in some sense where it exists, it means that solution exit of the stochastic differential equation is in a small neighborhood of the point where function v takes a minimum over boundary. So, and actually, let me define this function u of xt by this formula. So you consider the event where first exit time is smaller than or equal to t, and take the probability. Then you see that this function of xt satisfies this parabolic differential equation, which is my equation. Also, because of this condition, if t is 0, then you have no chance to exit, so you have probability is 0, so you have initial date. If you consider initial value of this function, then it is 0. On the other hand, if you look at the point on the boundary and t is positive, then the solution of your stochastic differential equation immediately exists. So probability is 1. So for this function, you have initial data 0 and boundary data equal 1. And so I thought that this is what Friedling and Wenzel claim, that as epsilon goes to 0, you have this kind of asymptotic. And so this is more precise statement. And so it says that when I fix small positive constant delta and I choose compact subset of omega and take the limit as epsilon goes to 0, then the solution of the previous equation, previous boundary value problem converges to 0 uniformly on this space-time region. But you have to be careful that space region is changes as epsilon goes to 0. But usually when we say uniformly convergence, the domain is fixed, but you can you may understand by this statement uniform. So the difference 0 and this U epsilon is bounded by a small constant on this region as epsilon goes to 0. And similar result, complementary result is that U epsilon goes to 1 when in some sense complementary region with respect to t variable. But you have big gap between this value and this value because delta is raised to exponential function. So, but precise statement of Friedling Wenzel is roughly speaking this theorem. And so it is better to consider, easy to consider continuous boundary data and continuous boundary and initial data. So I take continuous function g, which is defined on omega bar. And then this is now my initial and boundary data of my parabolic equation. And maybe I switch here that, so far I assume that my diffusion constant coefficient is identity matrix, but let me switch to general case. And then we have this kind of general result. Not we, but maybe Friedling and Wenzel. And so this is almost the same statement, but we have G here. But here, G is G of 0. And this is, in some sense, smaller region, smaller time region, from not 0, but some small value. Delta is any delta, and then you cannot go beyond M0, but you have to subtract some positive constant from M0. Then you have this convergence. And then next statement is I assume that the function g is constant on the argument of function b over boundary omega. Then we have a similar kind of uniform convergence towards this value of g0. But now the time interval is from e to the power m0 plus delta over epsilon to infinity. So until up to this time, initial your solution converges to G0, but after some time from M0, your solution converges to G0. G0 is constant value on the boundary set argument of V of over boundary omega. And maybe I skip this part, but here I try to say that this theorem roughly claimed something, both of these results, this result, including this result. So exit position is somewhere close to the boundary point where it's near the argument of function B. So now, so basic assumption, so my purpose, so the purpose of the joint work is to give a PD proof for the above theorem. And we treat the general Aij, and we need parabolicity, uniform parabolicity of coefficient A of x. And then Hamiltonian H is, has this form. H of x is Ax times P dot inner product P plus B of x dot P. So this is now my Hamiltonian. And I try to keep outline of the proof of the main result. So it may probably boring you, sorry. But this is unfortunate part of another proof. I have to show a little bit about proof, otherwise. Anyway, let me write the equation again. This is my equation, and this is boundary and initial data. And my function G is assumed to be continuous. And actually, I need to think about, consider about the stationary problem too. So I would call solution of stationary problem V super epsilon. And maybe I use this notation to represent the operator from initial data to solution. Maybe just E epsilon is enough, I guess. So E epsilon G will be U epsilon, solution of this initial boundary value problem. S epsilon S epsilon G gives a solution of this problem. And so this is the first claim in the proof. And so if your initial data, my equation is linear equation, so I can take any, I can move around regarding the particular value. I like to be 0 to the center, so assume that G of 0 is something very close to 0. Then the claim is that by constructing some barrier function or super solution based on the function quasi-potential function V, I can show that U epsilon at the origin at time t is also close to 0 until some long time, but delta is some fixed small constant. And this delta depends on how G0 close to 0. And this asymptotics is for epsilon close to 0. So this is somehow close to the first claim in the main theorem, but this says only at the origin, not. So in the main theorem, the claim is when I fix a compact set omega inside omega, then I can claim convergence U epsilon to G0. But claim number one is just say that it is it is true only for at the origin. And then the second claim is something very similar, but so this is a graph of function v of x, quasi-potential. Then I take the level set y equal, I cut the graph of g by the level of lambda. And then you look at inside of this level, that is blue colored part. And then I project onto the level y equals 0. And so here is my domain omega, which is colored brown, maybe between pink and brown. And then purple color is the projection of this level subset, v less than lambda. And the second claim that if this level subset v smaller or equal lambda is contained where g of x is roughly 0. So function g is almost 0 where the color is purple. Then I can say that by constructing barrier function of super solution based on quasi-potential, I can say that the solution U epsilon at the origin is close to 0 up to time e to the power lambda over epsilon. So now once you fix lambda here, then you get to time scale e to the lambda over epsilon. So to make time interval larger, then you have to make the initial function to be close to 0 in a very big region inside omega. This is a second claim. And actually, what I say is that this is, we can do by constructing super solution based on function v. And then we look at the formal limit equation. We have epsilon coefficient epsilon inside in front of aij. So if you put epsilon equals 0, you get this simple, I forgot the name of this kind of linear first order equation. And our B is such that flow generated this function, vector field B goes to origin as t goes to infinity, so that if G0 is 0 at the origin, so and I'm assuming that G is continuous, so G is close to 0 in a neighborhood, small neighborhood of origin, and so when you fix a compact set and you solve the ordinary differential equation, x dot equal b, then you have finite time independent of the initial point for the ODE. You get to the in time t sub k, you get to your solution of ODE inside this small neighborhood of origin. That means that solution of this equation sees the value g0 or something very close to g0. That means very close to 0. Which means that at the time t sub k, my solution, original equation, a solution of my original equation behave like is approximately 0. The set on the set k, when epsilon is very close to 0, this is very standard limiting argument. So if you have enough large time, then and your solution is very close to 0 at the origin, then you can get in finite time t, you get to this value almost everywhere in omega. So if you combine this result, this is only for at the origin. But because of this, after finite time, you get to basically everywhere in omega, not very close to the boundary, but away from boundary, you get this you get 0 up to the time maybe something similar. For this time interval, just finite fixed time. So this way you can see the first half of the proof, maybe not proof, but the theorem. And then let me go to the second half of the main theorem, and then I need another construction of super solution. Tell me that when I fix small constant delta, positive constant delta, and compact subset omega, then I can find finite time, which depend only on k, so that sorry, this is what I was saying before. Yes, I gave the proof, but I suppose I have already explained. So let's go to the claim 5. And now I assume that function g is approximately 0 on the boundary. Then by a kind of construction of barrier function, I can say that u epsilon is again almost 0. Everywhere omega bar, but now time scale interval is some larger than or equal to the exponential to the m0 plus delta over epsilon. So now we are talking about time scale which is larger than m0. Let me call time scale larger than m0. And so please, so let me assume this, we know this. And then let me go a little bit further. And the next claim is that this one. Now gamma denotes that argument of function B on the boundary. And V0 is a solution of stationary problem. And the claim is that if function G is close to 0 on the gamma argument of function V, then your stationary solution of V0 is, at the origin, it is almost 0 when epsilon is 0. Actually, this is once very popular even in the viscosity solution group. And this is done by Peltam. And it was also all the result, Friedwin and Wenzel, maybe Kamin and others. And quite recently, not quite, but recently, Camilli, Cesaroni, Sikonov gave another proof and more detailed study. But here, I go very simple way, not very simple, but anyway, my claim is contained result from previous work, Peltam and Camilli, Cesaroni, Sikonov, and others. Anyway, we show this claim using this this kind of behavior of U epsilon. So for the stationary problem, we don't need the value of function G inside omega. So I may assume that maybe actually, this picture is now important. Oh, sorry, I'm a little bit confused, but G. I don't remember why. So basically, I can assume that G is 0, where I'm sorry. So this function is defined on omega bar, and this is about the behavior of function G inside omega. So this is a set inside omega bar, and of course on the when x is on the boundary, I can assume that G equals 0. But I can assume even inside omega by replacing another function G so that G is 0 inside this set. So this is just one, gamma is one point, and so I have V smaller, this sub-level set of function V, and G is 0, this point, and I don't know inside value of G, but I replace G to be 0 in the purple part of my omega function domain omega. And then I choose lambda to be a little bit larger than m0. And maybe this g almost equal to 0 means that maybe g equals delta. Delta is small positive constant. Then when you so if you replace lambda by m0, you have this, but because of this ambiguity, you can raise lambda to be a little bit larger. Then we have this claim. So initial boundary value, solution of initial boundary value problem behave like 0 up to the time e to the lambda over epsilon, when epsilon is very small. Now you should be careful. You should be notice that lambda is now greater than m0. Then I subtract with v epsilon. I subtract this solution of evolution problem from the stationary problem, and I call it W epsilon. Then, because of the boundary data for stationary problem and initial boundary problem, the boundary data is 0. And then I claim that in this situation, if lambda is larger than m0, then W epsilon is also solution. My equation is linear equation. This is also solution of my parabolic equation, so that my previous claim can be applied, and W epsilon is close to 0 everywhere in omega bar, and also t greater than this where lambda is larger than m0. So we look at the time when e to the power lambda over epsilon. We can apply this and this. So this is 0 almost, and this is 0 almost. So this is 0 almost, at least at the origin. So V epsilon is almost 0 at the origin. And if I apply again the transport equation, argument using transport equation, the origin can be replaced by any compact subset of omega. Anyway, this is the last claim in this outline, and so this is the second half of the main theorem. And so, yes, something exactly, not exactly, but now my boundary data on the gamma is 0. And then the solution is roughly 0 when time t is greater than or equal to e to the power m0 plus delta over epsilon, as epsilon close to 0, where x is inside in any fixed compact subset. And here is some comment of the proof of this. For this, I needed to switch to, not switch, but to use a stationary problem to make, again, the boundary data to be 0. So V epsilon is, again, solution of stationary problem. And then now W epsilon is solution U epsilon minus V epsilon. Then this function has boundary data 0. So I can get maybe claims 4 or something like that. W epsilon 0 is approximately 0 when t is in this region, when epsilon is 0, close to 0. But we know that this, so W is this difference, U epsilon and V epsilon, and this we know as epsilon goes to 0, this goes to 0, and this goes to 0 at the origin at this time scale. So means that U epsilon at time at the origin goes to 0 as epsilon goes to 0 if time scale is greater than m0. And then we can use argument by using transport equation so that 0 origin can be any compact subset of omega. And probably I don't have time, but actually I wanted to try to explain how to construct super solution, but I don't know if I can do. So this is a key argument for the second half of the main theorem. And maybe I just say that we consider this kind of Hamilton-Jacobi equation, and then the solution look like the graph look like this, but not exactly m0, but maybe a little bit larger than m0, but eta is some fixed positive constant. When eta goes to 0, I will choose in the proof eta to be very close to 0. And if I let eta to 0, then the height of the graph goes to m0. And using this, maybe not this function, but negative of this function, which satisfies maybe equality, h of x dw greater than or equal eta. But I need to kind of modification so that I just keep the inequality, this kind of inequality, and then after smoothing this function, final function, which I use as a super solution of my problem, is this kind of minus V epsilon. V epsilon is this function, e to the w over epsilon, then some linear term in t. And maybe let me finish my talk. Thank you very much for your attention.
Question, comments, remarks? Thank you. In Russian, question.
I shall translate. I shall translate.
Существует ли связь между временем наступления неустойчивости уравнения и квазипотенциалом броуновского движения?
If there is any connection between the time once the equation becomes stable and the potential of the Brownian motion. Whether no, I'm trying to speak English. Whether there is a connection between the time since the equation become stable and the potential of the Brownian motion. If there is a connection between the time since the equation becomes stable and the potential of the Brownian motion.
Наступление неустойчивости решения.
Sorry, when the equation becomes unstable. So there is a time when the equation becomes unstable. Yes? Is there a connection between this time and the potential of the Brownian motion? Of the Brownian motion.
I have no idea. Potential Brownian.
Он же рассматривает броуновское движение там или нет?
Do you consider the Brownian motion?
What do you mean by potential of the Brownian?
А что вы имеете в виду под потенциалом броуновского движения?
Квазипотенциал Венцеля, это там же эти броуновские.
Венцель he means the Венцель quasi-potential.
Вот броуновское движение, видите у него там, вот.
And where is где потенциал?
А квазипотенциал там, в Венцеле там есть квазипотенциал Венцеля.
У него есть?
Есть. Выше? Ниже, по-моему. Квазипотенциал Венцеля у него есть.
He says that you introduce the Венцель quasi-potential.
Yes.
So he calls this Венцель quasi-potential the potential of the Brownian motion.
Quasi-potential as potential of Brownian motion.
Yes.
Можно забыть о броуновском движении просто между квазипотенциалами неустойчивости решения.
Okay, he reformulates his question. Could you please say anything about the connection between the instability of the equation and the Венцель quasi-potential?
Связь существует или нет? Максимально
У него нет на эту тему мыслей. Может быть, вы это обсудите в кулуарах. Okay, he will try to discuss it with you in person.
I have a short question, Hitoshi, about is it essential to assume uniform parabolicity for this kind of results? Or so if the Brownian motion degenerates, things could change a lot?
So at least technically, I don't know what happened for quasi-potential.
Quasi-potential becomes convex with flat, maybe flat parts. You didn't read.
I didn't consider
Okay.
in that direction.
So if there is no more comments, we thanks again Professor Ishii.
Thank you.
Thank you. We have a coffee break.
Before the coffee break, we have a very short but very important announcement from the organizers.
Dear participants, please note that the opening on the workshop starts at 15:25 today in this room, which is 5 minutes earlier against the time from the printed program. Dr. Jorn Achterberg, the representative of Deutsche Forschungsgemeinschaft in Russia, is going to say a few words about the DFG activity. Thank you.
I'm pleased to be here. I enjoyed very much the invitation at the previous DFD conference 3 years ago. So I liked the atmosphere, the scientific atmosphere. And so I'm particularly pleased to have been invited again to contribute to this conference from our German and, of course, Russian colleagues in the scientific committee. So today the title is very generic because it was the title given a long time ago. So I try to be a little bit more precise in the plan of my talk. And anyway, the theme will be some properties of a fully nonlinear degenerate elliptic equation. And the emphasis is rather on degenerate, in a sense that will be made precise in a few seconds. Maybe I have to switch on.
Yes, you can take it off. And
okay, it's better. Okay. So, as I said, my original plan was to present some recent results obtained by myself in collaboration with other colleagues. Most of them are in the conference. Concerning viscosity solutions of partial differential equations, which are governed by a fully nonlinear degenerate elliptic function f. The two topics were quite different, but the thing in common was nonlinear and degeneracy. And the first topic was to present some new results about the necessary and sufficient condition for the existence of entire solution defining on the whole space of equations such that in the middle line. So it's a function of the Hessian of a known function u. There is a gradient term, which is a power for simplicity of the gradient, of the absolute value of the gradient, and then a semilinear term f. And the other topic was the validity of the sign or propagation property or maximum principle, you can call it. Suppose you have a function u satisfying the two inequalities f of the Hessian of u less or equal than 0 in some domain, and u less or equal than 0 in the boundary. The question is, under which conditions on f this implies that the sign is propagated inside u less or equal than 0 in the whole of omega. And okay. For the first part, the results have been obtained in collaboration with Fabiana Leoni and Antonio Vitolo, who are in the audience today, and they will give talks in the afternoon, and are contained in these papers. One is in a volume dedicated to Neil Trudinger, recently appeared, and the other one is a submitted paper, which present more general results. And the key things about this topic is that we discussed this question, this existence, necessary and sufficient condition, by establishing some generalized version of classical, I would say, Keller-Osserman integrability conditions, which in the classical paper of Keller-Osserman does not appear the term with G, with the gradient. And so we establish a new version which involves condition, joint condition on both the nonlinearities G and F. And I guess that Fabiana Leoni's talk today will touch, at least in part, this topic, so I decided to be shorter and to be more focused to discuss here today in this talk the second issue. In reporting some joint research with Henri Berestiquis, Alessio Potetta and Luca Rossi, who is also here. And we have still a preprint, which is in archive, and you can consult it if should you be interested in these topics. Let me go into the problem. So about sign propagation of maximum principle in our framework. The framework is as follows. We start with the bounded domain in Rn, and we have a function f, capital F, which depends on the position, on the state, x in omega, on a number r, which stands for the value of some unknown function u at point x, p is for gradient, and capital X and y are matrices, symmetric matrices, n by n, and y non-negative means y non-negative semi-definite. And the assumption of the generated ellipticity can be stated in general is an assumption concerning the behavior of capital F with respect to the matrix slot. And it's written there, it's a monotonicity of F with respect to the partial order of matrices. So f of x plus y is less than f capital X if y is non-negative. And this can be given in different forms. This is the simpler and more general. The basic example you have to keep in mind is, of course, that of linear operators, like here, in non-divergence form. TR means trace, and you have a trace of the product of a matrix A, which is non-negative definite, for the Hessian matrix of U. And then you have linear terms, transport term B dot scalar product U, and perhaps minus Cx of U times U. This is the basic example of the generated elliptic F. It's, of course, is a more general case of the uniformly elliptic operators, which corresponds to the case where A is positive definite. So it's strictly convex. The quadratic form is a strictly convex paraboloid. So this is the basic example. We see more examples later. So to be precise, I will say that F satisfies the maximum principle or the sign propagation property in a set omega if for each upper semicontinuous function, USC means upper semicontinuous function, satisfying the two inequalities in brackets, so the differential inequality F less or equal than 0 in omega, and the inequalities for U less or equal to 0 on the boundary. So in some sense, this U is a viscosity in terminology of viscosity solution, is a viscosity subsolution of the Dirichlet problem. So F satisfies the maximum principle if any such function U is non-negative inside. So the sign on the boundary is propagated inside, is enforced inside by the validity of the differential inequality. And it's important in this work to consider, because of the general ellipticity, it's mostly appropriate to consider the boundary condition to be satisfied in some relaxed sense, in the sense of viscosity theory. And by this, I mean the following thing. U is a subsolution of the Dirichlet problem if we all test function phi, smooth function, and maximum points psi of the difference. If you test the function, the equation, the differential inequality at the gradient phi and Hessian phi, which are well defined because phi is C2, and while U is perhaps only upper semicontinuous, then this is less or equal than 0, and the maximum, well, the second line inside, And at the boundary, the condition is that the maximum between the values of u and the values of this is less or equal than 0. So both are less or equal than 0. And this is what in viscosity theory is called relaxed viscosity sense. I don't comment more on this point, but this is important when dealing with the degenerate ellipticity. Maybe I should say that when the assumption of degenerate ellipticity I wrote before includes the case of first order operator. I mean, the function f may not depend at all on the second derivative. Of course, that condition is satisfied for linear first order operators. So the Dirichlet problem, it's well known not to be well posed, and so this is the appropriate notion for, one of the appropriate notion for Dirichlet problem, Dirichlet condition. This is for the differential inequalities. Now, so let me say something about the principal eigenvalue. It's well known, there are a lot of literature in classical linear setting that the validity of the maximum principle is related to a sign of a number, which is the principal eigenvalue of the operator. It's related to the positivity of this number. And these principal eigenvalues, for example, for linear self-adjoint operators, can be defined by this variational formula, the Rayleigh-Ritz. You minimize the quadratic form of the linear operator under constraint on the space, Sobolev space H10, for example, if the Dirichlet condition is 0. And this is a well-known notion and well-studied, of course. And the generalization of this notion of principal eigenvalue was proposed by Berestiki, Needham, and Varadan, maybe in '94, I guess. And they considered the linear non-divergence. So, of course, this Rayleigh formula makes sense for if you have a variational structure, so a divergence form of operator. If the operator is not in divergence form, this formula cannot be written in any reasonable sense, and so they give a different definition. The definition of generalized principal eigenvalue is in the following next line, is lambda 1 is the supremum of all real number lambda for which you can find the W2n, a Sobolev function, which is positive in omega and satisfies f phi, means f x, phi x, d phi x, d2 phi x, minus lambda phi positive. It's a super solution of that equation. This is in almost everywhere in omega. This is the Berestiki-Needham-Varan definition. And using the notion, they were able in that proof to extend the classical characterization. So under this notion, for that class of operators, the maximum principle holds for, maybe classical is wrong there in the statement, for strong solutions, strong Sobolev subsolution of the Dirichlet problem, if and only if their number lambda 1 is positive. And this was proved, as I said, for non-self-adjoint operator, linear operator, and most important, perhaps, even in non-smooth domains. And this is a basic result in this circle of ideas. And what we address, the question we address in this joint research with Berestiki, Alessio Porretta, and Luca Rossi is there is any way to extend the validity of that result to fully nonlinear function f's, and also perhaps possibly degenerate elliptic. Remember, the Berestik-Nierenberg holds for linear uniform elliptic operators. Of course, at this purpose, one has to produce first a good notion of principal eigenvalue in this setting. And we started by looking by literature on principal eigenvalues in the fully nonlinear case. This is a partial guess, but bibliography of this subject, but there is not much literature on that. I think the first paper is by Pierre-Louis Lyons. There is a paper by Professor Ishii and Yoshimura, and both of them concern, if I'm not wrong, equation of Bellman type, so that the structure of F is convexity with respect to the Hessian matrix. And more recent work by Isabella Birindelli, who is there, and François de Mengel, Stefania Patrizio, who is also here, Yutinen, Quas, and Sirakov. I come back on the work of Birindelli and de Mengel in the sequel. All these papers dealt with the, if I'm not wrong, please, if I'm wrong, please tell me, with the uniform elliptic case, with the important exception of Birindelli de Mengel, who consider some singular operators, which, so there is a degeneracy, but not the same of degeneracy which I'm interested in today. And they modified the definition by Berestik-Nierenberg-Varadan in order to deal with a class of operators which are positively homogeneous of degree alpha, positive degree alpha, which is almost a necessary condition to discuss eigenvalue problems, as you can imagine. And they were able to treat several nonlinear operators, and also the example of pre-Laplacian and variants of it. Okay, their definition is as follows, is similar but different to Berestiki and co-workers, and lambda 1 is the supremum of all the real numbered lambdas for which there exists a lower semi-continuous positive super solution of f phi minus lambda phi alpha greater than or equal than 0. So lower semi-continuous. And maybe this is another variant, it's a little bit different definition where phi positive is replaced by infimum of phi positive, strictly positive. Maybe this is a side remark which says that perhaps if you have a degeneracy, perhaps a natural way is to work on elliptic regularization of the problem if, by adding a term like minus epsilon Laplacian to your operator in order to Tikhonov regularization. There are several ways to call this approach. So perhaps a natural way is to look at the classical principal eigenvalue of the elliptic regularization and then try to take a limit as epsilon goes to 0. This notion has some relation, but they are not always the same. If f is uniform elliptic and smooth coefficient, then the possible notion of a generalized principal eigenvalue coincide in the standard uniform elliptic case. In the general case which we want to treat, which includes also first order operators and even zero order operators in the limiting case, none of this notion works satisfactorily. So you can produce, for each of these conditions here, This is the two Birindelli de Manger condition. This is the second one is the limit of elliptic regularization. For each of the following of these conditions, you can produce a degenerate elliptic operator for which the number lambda 1 is positive, but the maximum principle does not hold. So, so this is a phenomenon related to degeneracy, of course. These are, I have some example, I think I don't have time. Simple examples show this. I don't have time to discuss in detail, so please believe me that this is true. So the first step, real step, was to identify a right notion of principal eigenvalue working, hopefully, in the degenerate case. Let me mention that the result that I will state in while it seems to be new as far as we know, even for linear equations, linear degenerate elliptic equations. So it's these phenomena are typical of degeneracy. They are not due to nonlinearity or brutal nonlinearity or no regularity of solution, of viscosity of solution. They are intrinsic to degenerate ellipticity. So the definition we gave is that one sounds a little bit strange at first, but I try to convince you that it works. So we have a domain, open set, or O, cal O, which includes strictly the closure of omega bar. And then we have a positively homogeneous operator of degree alpha. And we define this number mu1 by a similar procedure. We take the sup, the maximum, the sup of numbers lambda for which there exists a domain omega prime which is strictly bigger than omega, including omega, a lower semi-continuous function phi, which is positive, satisfying the natural inequality f phi minus lambda phi alpha positive in omega prime. So our definition of mu1 requires the operator to be defined in a larger set, which includes strictly the boundary of omega, where degeneracy may create problem, because of boundary layers, well-known phenomena for degeneracy. This is the definition of mu1. 3 short remarks. Our number mu1 is the supremor of the numbers lambda 1 of previous slide with respect to sets omega prime containing omega. And is also the limit, maybe this is more transparent, you take your omega, you put balls of radius b epsilon, and you construct the set omega plus b epsilon, and take epsilon go to 0. And this is mu1. And for smooth domains, a uniformly elliptic f with smooth coefficient, again, in this case at least, we can prove that all these numbers are the same. While in general, there is this inequality, mu1 less or equal than lambda 1 bar, lambda less or equal than lambda 1. And of course, this is quite unpleasant at the beginning. Our definition requires the extension of f on a larger domain. But the result that we proved shows, in fact, that this notion of mu1 does not depend on the particular extension. So in the end, it's acceptable. So our main result is like this. Take again omega bounded domain, not necessarily smooth. If smooth, in the last slides I make some comment on smoothness. Calligraphic O is an open set which contains omega bar. Assume that F is continuous, degenerate elliptic, positively homogeneous. And that it satisfies this big matrix, this condition. And I'll comment on this in a second. Under this condition, we have the desired characterizations. So F satisfies the maximum principle in omega if and only if that number mu1 is positive. So the basic assumption are, as I said, continuity, degenerate ellipticity, and positive homogeneity. That big assumption, quite difficult to be read at first, is an assumption which, as you can see, concerns essentially only the behavior of F with respect to the matrix slot, Fy minus Fx. The other arguments are the same. And this must be satisfied if the matrix X and Y satisfy the matrix inequalities above. I don't have to comment. I don't have the time, and it would be inappropriate to comment on this assumption. This important, very important structural condition was introduced by Crandall, Ishii, Professor Ishii here, and Lyons to prove a general form of comparison principle for fully nonlinear degenerate elliptic equation. So we take it as a basic tool for our work. And as I said, for example, it is that assumption is satisfied in several situations. For example, for linear equation, is satisfied if A is the is non-negative definite, sigma tau sigma with sigma Lipschitz. And it's satisfied also by when matrix A equals 0 by aconal type operators, and there is a lot of literature on this. So this is a basic, the main brick to prove, to have comparison properties which we need in our proof. And it is a very solid tool on which one can rely, very general. These are examples of operators to which that our theorem, characterization theorem, applies. I go fast. There are proper operators when F, for example, is, well, I don't have to. First order operators, sub-elliptic operators. For example, if ellipticity, uniform ellipticity is not assumed, but there is some non-degenerate direction in the space. So for, which is expressed in the first formula there. F as a function of the, if you add to X some product psi in some vector, unit vector psi, and this difference is strictly negative, so it means uniform ellipticity, if you like, in the direction psi. Degenerate ellipticity as a whole, and uniform in the direction psi. In this case, you can prove that the principal eigenvalue as we define it is strictly positive. So the maximum principle holds by virtue of our results. Other class, interesting class is a class of one homogeneous degenerate elliptic Hessian operators. I call it pk. It pk of some matrix D2U is the sum, or with minus sign in front, is the sum of the largest eigenvalues, largest k eigenvalues of the matrix itself. So you don't sum all the eigenvalues, but you sum only some of them, the largest one. This is the degenerate elliptic, satisfies all the assumption of the theorem. So the maximum principle holds for this operator, which have been considered, introduced, I guess, considered by Harvey Lawson in a series of recent papers. The other interesting example is perhaps the maximal Pucci operator in the degenerate form. And this operator is the sum of the positive eigenvalues of the Hessian matrix, with minus sign in front to have the general ellipticity. Usually, the standard Pucci operator have this form. You make an average, sum of positive and negative eigenvalues of the Hessian, and they are weighted differently by capital lambda and small lambda. The operator this is uniformly elliptic if small lambda and capital lambda are positive. Our example corresponds to the case capital lambda equal 1 and small lambda equal to 0. This is degenerate. Again, we can compute the number mu1. Therefore, the maximum principle holds for this operator by virtue of our theorem. The P Laplacian and infinity Laplacian fits in our assumption. For these operators, the work Birindelli, De Mangel, and Newton established the result before us. But our approach includes also this case. Excuse me, I want to check. I have 10 minutes or less? Huh? 15 minutes. So 15 minutes, think I'll give you a short outline of the proof. So the theorem says that under some condition, the positivity of number mu1 is equivalent to the validity of the maximum principle. So there are two implications. First one is, in this sense, mu1 positive is implied MP. And this is the easier between the two. This is a very compressed sketch of the proof. So I hope it gives an idea, however. If mu1 is positive, then by definition, by very definition of mu1, you can find a number lambda positive, a set omega prime, and a semi-continuous function phi, such that phi is positive, and phi is a super solution of f phi minus lambda phi to the alpha in omega prime. So suppose by contradiction that the maximum principle does not hold, and therefore there exists a subsolution U which is positive somewhere in your set omega bar. This is the contradiction. So the first step of the proof is to show by viscosity calculus, which is standard viscosity calculus, I would say, but you need viscosity calculus, that the function u tilde, which is the max between u and 0 in omega bar and extended by 0 outside, satisfies the inequalities f u tilde less or equal than 0 in omega prime. And this is a computation of testing with a suitable smooth function to verify the definition of subsolution. Then we use, again, a typical tool of the viscosity theory, the doubling variable, to double the variables, and consider an auxiliary function, which is the difference between your u tilde and the function phi of the third line above, minus perturbed, penalized by n half n, norm of x minus y squared. The penalization terms, if you look, well, it's useful to force x to be close to y in the minimization. And then, working on this function phi and using the comparison principle mentioned before in an essential way, after some computation and taking limits as n tends to plus infinity, allow you to show the existence of some point z where your function phi is less or equal than 0. And this contradicts the fact that phi was strictly positive. And this, omitting all the details, is the structure, the skeleton of the proof. The reverse inequality, MP, maximum principle, implies the positivity of mu1, is more delicate. And the very core of the proof, to be short, consists in showing the existence of a function capital U, upper semi-continuous, non-identically 0 and non-negative, satisfying the satisfying this pair of conditions. In the relaxed viscosity sense, this is crucial. The relaxed viscosity sense I mentioned in the first, second, third slide, in the very beginning of the talk. At this purpose, we adapt a method which has been proposed by Birandelli de Mangel in their paper I mentioned it before, to 2006 or 7. We have to adapt the method to take account of the typical difficulties due to degeneracy. We do not assume existence of barriers for our problem, so the degeneracy can be hard to deal with. Very shortly, omitting many details, even a little bit delicate, we consider a sequence of smooth domains omega n in this way, and function phi n with positive infimum, and look for subsolution of this equation, which is the typical eigenvalue equation at a level a little below the eigenvalue level, the principal eigenvalue level. This is the main idea, and using again another big, strong tool of the viscosity theory, the Perron, I would say Perron-Ishii method to construct solution by taking maximum of a subsolution, and also several tools, other tools of the viscosity methodology, like stability or in some refined form. We can build a function U, capital U, satisfying all this. Then, so almost everything is done. You have to check in the end that U satisfies the boundary condition in the relaxed viscosity sense. This requires some work, but it can be done. Once you have done that, and I've been very, very short, you immediately deduce that the validity of maximum principle implies the positivity of the eigenvalue mu1. This is would take some more time. This is, in fact, more an open problem than a remark. One could think that first, that the function capital U, which I constructed in the previous two slides very rapidly, is a good candidate to be in an eigenfunction, the principal eigenfunction corresponding to the number mu1. This is not true in general. First, because essential of the generality of our framework. In the uniformly elliptic case, this is true, because mu1 is the classical eigenvalue and everything, and you have compactness, Green-Rootman theory, everything you want. In our setting, the number mu1 can be plus infinity, for example, for the operator first derivative in one variable. Our eigenvalue is plus infinity, so there is no hope to have a solution eigenfunction corresponding. Even if mu1 is finite, the principal eigenfunction may not exist. And this is one example for which the number mu1 is 0, but the unique putative possible tentative eigenvalue, eigenfunction, corresponding eigenfunction is identically 0, so it's not, cannot have the role of principal eigenfunction. In case of barrier, in case of barrier, things are more simple. By barriers in generalized sense, the definition we took into account is that one is a function, a continuous function, which at some point of the boundary, you can find a ball and a negative function w, the barrier, which vanishes at that point and is a super solution of fw greater or equal than 1. Essentially, under this condition, we can prove that our strange eigenvalue is not so strange, is the number considered before by previous author, which I mentioned. Perhaps more interesting is to finish with this two short comments on linear operators. As I said before, our characterization theorem, I think, and I'm pretty sure, that is new even in the linear case. So saying something more on linear operators, it might be interesting. So consider the linear operator, which is up there, where matrix A is positive semi-definite. So it's, we are in Russia, the main reference for this operator is the book of Olejnik Radkevich, as far as I know, at least. I learned things on that book. So positive semi-definite. Operators of this kind were also been studied in my university, in my department, by Fichera in 1956. And he considered this kind of condition on the boundary, which is called by now Fichera condition. The Fichera condition is satisfied at some point of the boundary if either of the two following holds. Either the first one is that you consider D, the sign at the distance from point this is the sign at, but there is a mistake in the notation. The sign at distance from the omega. Convention take it to be positive inside. So if the quadratic form, which is there, the gradient is positive, or if it is 0, this is the only other possibilities for semi-definite operators, then this expression must be strictly negative. So this condition was introduced by Fichera, and what we can prove under this condition is the following result. So if the Fichera condition is either always satisfied by your domain omega and by your operator, or always violated, then the two numbers mu1 and lambda 1 star bar of the initial slide are the same. So this is a case where even this was the fact that they were the same. It was known. It was stated to be true for uniformly elliptic, degenerate, smooth things. In this case, we consider also a smooth domain, but a degenerate operator. If the Fichera condition is either always satisfied, always violated, then the two numbers are the same, and this is a connection with previous research on, and this would be interesting to extend this condition to nonlinear setting. I'm finishing here, hope not to have gone too far, and thank you very much.
Thank you very much for your interesting talk. Are there questions, remarks, please?
He speaks Russian.
Какой смысл иметь вязкость в стационарных уравнениях?
What is the sense of the viscosity in stationary equations?
The sense of viscosity is given by the, technically, formally is given by the definition in the first slide. More intuitively is that you, for linear equation, for example, the sense of viscosity for linear first order equation is you take a first order equation like Hamilton-Jacobi, you add an epsilon Laplacian term, like viscosity term in physical meaning, solve the second order equation, which has smooth solution perhaps, probably, and then take the limit as the viscosity epsilon goes to 0. And this gives the generalized notion which I used.
Это технический прием, то есть вы берете уравнение...
Математический прием, правильно? Технический, математический прием.
Да, то есть, ну, метод исчезающей вязкости.
Я так и подумал. Ага. Спасибо.
He guessed the same.
I have a question. Do you have also something like an anti-maximum principle in this case?
No, not for the moment. I'm not an expert. I have an expert here on anti-maximum principle. No, we didn't work on this, but it's, of course, it's nice to investigate.
Since you called lambda, you put the 1 at your lambda, do you expect that there will be a lambda 2? No.
I know that Birindelli and Patrizio are here. They are working very hard on this topic for fully nonlinear equation. If you need information, you can ask her. But I think it's very hard, as far as I know, it's a very hard. But 1 is for having 2 later, of course.
Can I just mention one comment? Interestingly, in the famous work of Berestiki, Nirenberg, Varadan, the approximation of the domain is but is not done by the outside, as you do here, but by the inside. So
yes.
They approximate domain by filling up the original domain.
Right.
So it's quite interesting that here, on the other hand, you need to do the contrary in order to obtain a similar result. So like if the regularity needs to come from the inside, while the degeneracy needs to enlarge. It's
in a sense, this is the point. If even, I mean, for a regular domain, with the degeneracy of the operator, the Berestiki method does not work. At least we are not able. We had to consider larger domains. So this is, I think, this is the effect of 2 different actions.
Further remarks, questions? If this is not the case, thank you again.
Thank you.
And we shall continue in 5 minutes.
Now it's here. Okay. Ready?
Yes. Just don't touch this.
Okay.
So you use this only as a pointer.
Okay.
This button, okay. And the microphone is here. Okay.
There we go.
So I think we continue. It's the second time in my life that I have the pleasure to introduce Professor Willi Jäger from Heidelberg in a big conference. And today he will speak on systems of functional differential equations, modeling the dynamics of structures, population, modeling, analysis, and applications.
It's a great pleasure for me to have you as a chairperson. I cannot say chairman. I choose this topic, which is totally different from that what I was talking about in last sessions, because I think that this kind of problems have to get more attention by mathematics. Structured populations, in a certain sense, have been available all around, but also the equation for that, it has gone also fashionable in a certain, some type of equations have been gotten in the interest. For instance, Bertham is doing a lot on systems of nonlinear, not systems, single equations of nonlinear structured populations, just single equations. But what I want to stress here is, and also give you an existence proof for some situation which we treated, at least indicate how it's done. Now, important it is to consider systems of structured populations with many structural variables. The problem usually then is we cannot treat so many, but in the problem given, there are many, and we have to find methods to reduce them, and this will be on the end, the challenge which I would like to pose to you. And usually these structural variables lead also not just to PDEs, but to functional differential equations because of these structural distributions. Now let me start. Here I give you a certain survey what I want to treat shortly. I will just say something in the beginning, and that what I took is also gives you some thing, some insight in our lab. What we are doing is modeling of structure for populations and able to choose examples from life science. In fact, originally we were also very much interested. A lot was developed for polymer chemistry, for instance. A lot of work has been done there. One structural variable is for linear polymers, for instance, the length. And then I also will give you some example for drug resistance, which we recently did for malaria. It leads to a system of equations, a special one. I have to confess, it's not the most general one can think of, but already general enough that it has not been covered by any contribution in the literature, which we used then theoretically for this drug-resistant problem for malaria. And then I want to say something about what are the possible generalization and what are approaches to numerics. And then the main thing is finally, I really try to get your attention to the mathematics which is needed, maybe also analysis combined with numerics to reduce those problems. Now let me start. Mathematical modeling of structure. I show you first one population. Think already of a system of populations in biology, but you also could do it in sociology, wherever you want. You have a population, they are moving in space, particles, cells, agents, and they are living in a certain state space. And I give you an example where what are typical state space. We have now molecular biology informs us a lot on cells. A lot of ours, and they will show you how complex already the dynamics of a single cells can be. But we are not interested in single cells. We are interested in populations. And the first thing is, if I know dynamics of single cells in space, in state space, how get a model equations for populations? And this is a challenge which everyone knows. It could be done also combined with stochastics, many particle systems, and also new problems where we cannot take the assumption which we usually have for many particle systems that, I mean, for instance, in a channel are a lot of particles. We don't have this in biology. And you can model the state space in a discrete way, but then you end up with large systems of classical partial differential equations. Then you can say, I have a larger system and how to reduce it. But as soon as you have distributions in the state space, for instance, length or age or other concentration of some receptors on a cell surface, then you have automatically continuous structural dependent additional variables. Here I give you one example where you can see what the problem is. In fact, when we looked at this, we found out, I hope it's again the effect that the movie doesn't work on this. Usually this happens with a wrong transmission. Let me tell what happens. These are stem cells, and the stem cells usually have come from the blood, going into they have to move in the bone marrow. And what we have here, what I can show you afterwards, but usually in some situation of these machines doesn't work, doesn't connect to the movie. And then what you see is they move, you have a gradient of substance, and activated, and they move from this side to the other side. And the problem, how do they do that? We have now, yes, where is it? I don't have it. Here. Give me that. Okay. Then you do the following. In fact, these experiments are made. We are concerned with these experiments. And then you know what happens. For instance, the chemical substance is known, also the receptor. But how to describe a single particle you can do, but you do not know how to describe that as a population. Now, I'm very sorry that this movie does not work here, but sometimes this happens. And there you see down here, maybe also this also does not start. it's done now. You go, if you do not introduce structural variables, because we cannot receptor distributions in it, then you get the chemotaxis equation. In this case, I also want to mention that here, because a lot of people consider now chemotactic equations because of these beautiful explosions which I show afterwards, but they are not really related to the real life problems. Here we have the problem. The nonlinearities are not inside, they are on the boundary. And there's really necessary knowledge to do that. But here we have not the situation of structural variables. But I wanted to just to tell you, it's necessary to introduce them already in the case of chemotaxis, which we know now a lot by microscopy. In fact, all this, what I show you, it's done in Heidelberg. We have a huge center together with biologists. We also have a lot of microscopy. We can look what happens with single molecules in cell. We also can see how cells crawl and move. It's accessible, but it has to be transferred to mathematical models on a higher scale. And there I really want to make commercial for that, to go inside this kind of problems, because it creates new mathematical problems also to many limits of many particle systems we had in the lecture of Professor Kozlov, the billiard, but here we have more complicated situation. We not just have interaction, mechanical interaction, we have chemical interaction all included. It's more complicated than the normal situation there. And I show you just for what you see here is not a subway system or channel system in a map in a city, but this is the networks which are known to happen in cells. It's a so-called Roche map, and if you zoom in, then you have here some network, chemical network. That means here we have a lot of complexity which we cannot resolve. But the molecular biologists are studying all this stuff. We have to think of these chemical nets give different rise to different states already inside a cell, which we have to describe by, if you want to understand populations. And here I give you just the famous Keller-Siegel model, which has been also related to the lecture of Professor Wei, because here, if you study special steady state solutions, then you have just these nonlinear equations where you have some nonlinear exponential of u or a power of u, which depends on the kind of the chemotactic factor. Now you see that. We showed that, Stefan Luckhaus and I gave the first proof that those kind of equations may lead to singularities. Here you see more than a delta distribution. There are a lot of things squeezed off, but this is not what I'm interested here in, but I just want to mention that and maybe attract some people who are working on that to another part, because we know in the meantime, just take it as a picture. I will shortly only describe. We have information what happens inside a cell, inside, for instance, E. coli, how it moves. And first of all, don't take the mistake. It's not necessary to detect gradients, only to detect changes. Changes of concentration. Changes can be also in time. That means you're just looking at the changes of direction because of relationship of changes in gradient. It's not good enough. Here we have, depending on the movement, if, for instance, you have a constant concentration race, the cell looks like if it would be a gradient if it moves, because it finds out in the other part it has a different concentration value. But therefore comes in also in the decision where to go and how to react, comes in the whole trajectory. And here what you have, you get an information on the top. there's a receptor, and there comes in a chemical substance, the chemotactic attractor, then it creates reaction like phosphorylation, which creates a signaling to the flagella down, and the flagella starts to move. And the direction is decided by, or it may go in one direction, but it changes then depending on the direction you have been before in. And there, what you have there in this case, let me show it once more here. This is again up there just a sketch of the chemical reactions which are going on in a simplified way. What you have, motion of a bacteria is like run and then tumble and tumble. And the tumbling is described by the chemical processes inside, and in fact, mathematically, it's the following. You have a straight line movement. I hope this works. If this also not works, I have it. We have simulated all this stuff by stochastic processes. It moves straight, and then according to the concentration in the history, how it was measured, the concentration, you have a boson-like process of tumbling, which gives a phase change, a direction of change, and a change of direction. This is done now in a PhD work, which I have, trying to derive Mismanic particle approach to derive equations, which will not look just like we had Keller-Siegel-like equation. But where comes now structure population in it? The structure population comes in that these cells may adapt to the situation, and they do. If I would have had the chance to show you the dynamics of these stem cells, they adapt. That means inside we have a chemical reaction which changes the ability of the receptors to take that up. What does it mean? We have in the equation the chemotaxis factor, which came up in Keller-Siegel, changes. Therefore, you have to put this as an additional variable how this change it is. You can do it in a compartment model. It's done, I hope, on the next. No, this is this is a normal movie done by, but it doesn't work. Then let me describe what you should see. Those who are interested can show it later. Up there you have a start about bacteria starts, it does a tumbling process, it makes a stochastic movement, and then it goes, at a certain time, it goes straight in the direction what you see here as a gradient, and it comes close to the point which is on the left. It again switch on the tumbling process. Therefore, we have there some Levy-type process which has to be put from a single to a population. And this is done, and we also did I'm very sorry, we didn't check if the movies go, but this happens from some time, going from to different machines. And there, excuse me, let me go back. This, if the movie would work, would show you, we put gradients on both sides. It's now about 1,000 bacteria, and you already can have concentrations, C concentration. It moves into two directions. What we have to have is population and dynamic equations for describing the spread, including change of sensitivity with respect to the chemical substance. And here you have this situation transformed at first, which we did in a system of compartment, which is not totally correct, because we know this is a continuous description. We just did that for a compartment and has been studied. What you see here, you have a population, U1 to UN. These are let me say, the E. coli, and you have one substance, they orient to that, but they react with different chemotactic factor, and then, but they also move from one to the other. They at first start to be sensitive, and after some time they move with certain laws to the next sensitivity. This means this has been, or you have a system now which you have to study the existence and the dynamic behavior, which we did. You see, to each of these U's belongs one GI, one such chemotactic factor. And then is a problem how to go to then go, these are the non-linearities which we use there, and we could show existence and non-explosions if we assume, like here we have here Michaelis-Menten kinetics, that means it cannot explode. So let me just see. Now we go to densities. As usually you do it, you go to densities and you make the limit in that part to get equations for the density. And what you have then, excuse me, I have to go back again, you end up with this equation. You have now also diffusion coefficients may depend on this variable which describes the adaptivity. That's the diffusion changes with adaptivity. Adaptivity, you have a chemotactic factor there, and you have in addition this movement which was in the former differential equation. Was a system of reactive terms which transported from one to the other. This comes up as a first order differential operator there, and therefore you have suddenly now up there and down there you have a sum, because they all produce this chemotactic factor which we have usually in the case of Keller-Siegel. Therefore we have such a system which has not been studied up to now. No, there doesn't exist an existence proof. We are working on that, but all this study is very recent. Now the problem is also in other cases. What do we have next? I want to say something on this is where we really had to went in the problem of drug resistance spread in time, not spatial spread, because this gives an additional diffusion operator in space that we didn't want at the moment. We just had there the situation of non-spatial dependence, and the problem there is the following. You know, malaria is really something which troubles us a lot, especially in this belt around the equator. And the drug resistance is really a challenge now, because if you give drugs, then these pathogens change their reaction. And I just shortly tell you, we have here in this situation of malaria, we have two populations, and each population is split up. One population is a host, is a man, the other is a mosquito, Anopheles, and each population is split up in an infected and in a non-infected part. The infected part, we should not go too much now in the details, which you see in the picture, the cycle. We make it very roughly, therefore I jump over to for time reasons, do not go in the dynamics of this process inside a host, but just tell you, we have inside the host, we assume now we have densities of drug resistance, and so also for sensitive with respect to drugs. Therefore, we have, in addition to the normal time variable, we have the variables of drug resistant densities and non-drug resistant pathogens. And you have them in the hosts as well in the vectors in the mosquito. And then, let me just see there, what kind of equations will you get? Here you see the scheme, which we don't have to study too much here now, because you will see it anyhow. We also include infectious, then we recovery, birth, because they all are creating birth too, and then you end up with a system which looks like that. And there comes in also the functional differential. But no, this I just said, this is recent work which is contained in was first started in a PhD thesis with my former PhD student from Vietnam, Anne Li Di Tang, and then also in cooperation with Maria Neuss and myself, and we have published one paper together, which is not the structured population part. We also have a compartment part. It's published in Journal of Mathematical Biology, and now we have handed in for publication the theoretical part for the structured population, where Maria was very much involved, and the biological part is in preparation to be handed into a journal. Now, what we have here is two types of populations, and each has two species and two subspecies that would be here susceptible, infected on the host side, and susceptible and infected on the vector side, and structural variables side of time. Now you can sit down, put up your own mind how to model, for instance, the susceptible one. That's very classical done. The only difference is here we really have structural variables in it. The susceptible one, they have no infective materials. Therefore, they are coming from have ordinary differential equations, and also for U, which is the not infected hosts. And what we have here then, you have a birth, which is marked here, you see that. We have a death, and we have loss by infection and recovery. And all the time you have to integrate there in this part which comes from the structured population part. You have to integrate, in most cases we have to integrate via on the structural variables because they are densities. The same thing is true for now first comes, here is the difference. We have the infected part. We have first part is what you would expect by writing down the balance. If you go from the compartment models to diffusion to continuous model, you have a first order term, which of partial differential operator, which tells you how they move. We assumed here that they are nonlinear. Not nonlinear, it also could happen. In our case, it can be justified. And we also assume that they cannot degenerate. The reason is clear, because if they would degenerate in some parts, they would be similar to the situation of susceptible. We would have an ordinary differential equation. But then, as you will see, we could get problems, because for the ordinary differential equation, we have to assume initial conditions. But for this part, we have to assume, in addition, equations for unknown boundary conditions. And this, in our situation, was not the case in the general case which we considered now. Also, we did not allow that, because otherwise we would have another complication, which are very well known in conservation laws, that you have problems with boundary conditions. Here you have that, new infections, changed infections, and then you have death of infected, and you have transfer of the structured variables up there. These are all what you have, and the recovered infective. What you see here is a first order partial differential equation with functional terms. And we have to see that how we can do it, but we have a system now. Evolution of the non-infected hosts, and here you see what we assumed here, some kind of, which is reasonable to take this of Michaelis-Menten type factors there, and they are reasonable to assume them for these growth terms. And here you have the same for the infected hosts, vectors. But we have a problem, as I told you before. We have a problem. We need, in addition to initial condition, boundary conditions. Because at the boundary, we have, let me say, the equations are valid for functions which are defined in the positive part of in time and an Rn. And then for t equals to 0, you know them, but you have to put on the other borders, sides, you have to put boundary conditions. And usually for a single a variable like age in a population, you would have somehow controlled birth of new population. And here we assume linear relationships, which I could justify if I would have time enough. Essentially, they are contributions of the population. How many of these guys are born on the left hand or on the sides of this positive part of R times Rn. And here you also could take Lipschitz nonlinear functions, but we used that here, which was reasonable to take there. And the same is true for the other parts. Now, let's go off from that. We just do the following. We just forget the malaria and take the infected part we call U1, or some first part, and the non-infected part U2, and then we get such a, excuse me, U1, U2 should be the infected part. That means those who have structure variables, U3 and U4 have the no structure variables. And then we just look and try to see, can we use now, what structure does it have? In our situation, it can be rewritten like that, and then you see, just look at those parts which have structure variables. They look very similar, and therefore we thought we have to do that in a general way. Now we will look at structure in the future. We will look at a system which falls into parts of a population which has structures and evolves with functional differential equation, and another part which just evolves with ordinary differential equations. And the problem is how to solve those things. You would expect, oh, I can do it as in a single, for a single parameter case, and here you have this ordinary differential equations for the case of unstructured, and evolution of boundary values. Here you see where I have to describe values, or I cannot describe them, I have to describe relationship. And what kind of relationship you will have, that depends on the application. And then you have to, in this case, would look like that. There are integral relationship where you have a U2, and you have, inside you have these functions U2 and U1. They are the solutions of the differential of the structure population equations which come up at the boundary, which give birth to the boundary values. And then let me just continue. Now let's reduce it. Let me just tell you, if you look at scalar equations, there has been a lot of study for nonlinear systems, also with birth structures, also one structure variable, several structure variables, also with some with spatial spread, but for systems, I'm sorry to say, we could not find things. And then we got a letter of our referee and for this paper, and he said, oh, the paper science is okay, but the proofs are okay, everything is okay, but can you show that it does not already exist? This is, giving such a non-existence proof is not easy. But we looked very carefully, and since I have very close relationship, who was very much involved was Otto Dickmann and Mats Gyllenberger, my former PhD student Horst Thieme. And I had asked them, does it exist? No, it does not exist. And the methods which they use are adapted to those types of equations, and they are not using this what is more old-fashioned what we had to do there. They use a lot of function analysis. They also prove measure valued solutions, which is important, which we do not do now here. But what we try to do is using the methods of characteristics, because this was clear that we should have some, should be able to do some, to be able to solve this problem in the way as we had needed it. You can do it in one scalar equation, it's clear, but then you have it simple. You have one characteristic. But here you have for each equation another one. Therefore, if you have, for instance, one equation and one structure variable is time, your age, then it's simple. You see everything. But here, you think it's simple, but it's not so, because you have to look all this transformation in each equation differently. You have to estimate them. What you would do is also clear. I mean, you really already hopefully see in which direction to go. Let me just, before I do that, let's consider the system. And this system looks down like that. You have a first part up to n. You have structured and linear terms which give in this first order is linear. It doesn't depend on the use. And then the right-hand side we assume functional. Essentially Volterra functional, it's clear, it depends on the past. And also what you would do, you would, with a proper norm, you would ask for Lipschitz continuity. And in this case, we also used global uniform Lipschitz continuity, and the reviewer again said, oh, that's terrible, it's not fulfilled. But very often what you have there, as you know, you assume a result for you prove a result for uniform Lipschitz continuity where you can the Lipschitz constant take large as you want. But for your application, you cut off and use it for existence. And if you have a solution, you show that the bound is below the cutoff. And this is the trick, as we always do it, but it depends on the application. Therefore, we didn't just mention that we can be able to do that. And then we have this part. The other part is the ODE part for the dynamics, again with Volterra functionals. And then we need positive solutions. And you have to find good conditions, reasonable condition to keep the solutions positive, because creating negative conditions would be a nonsense for the applications. And there is open problems immediately, because as you know, if you have systems, to get positivity, you may have to also give structural conditions depending on your application. We used the simpler one because we wanted to get not in specific applications in this case. But everything what we used here was we could be able to show for the to show in the case of malaria. What you see then, it's the boundary condition. We have to give boundary conditions. And there you have, it's written there, A marks that you are working on the boundary. If you have X and Y, then you work inside. And it says a relationship between the A's on the boundary and the functions inside. The functions inside are solutions of the initial boundary value problem, if you know the boundary values. And this is the problem which we have, but in order to show that, you have to have also good norms. And I do not go into detail, but it's clear, you know that from ODEs, you have to take weighted norms, because you would expect exponential growth, and therefore you have to multiply with good exponential terms to catch those things, and this is also has to be adapted to this special situation, and it's technical work which can be done, but it needs to be done. And then we have this at the boundary. These are the sections at the boundary. the sides of the boundary. And then conditions for the functional term. I have said it already, and with some properly defined norms, with some properly weights, we use the Lipschitz continuity, Lipschitz estimate for the functionals. So, and this other part we need for positivity. The function must be estimated from below to a multiple of ui. This is the assumption we take. Otherwise, we would have to use some additional structural continuity. But you know already how one uses with a proof, because everywhere when we show positivity where such a term pops up, one just estimates it from below, and then you take the usually tricks to show by exponential ansatz that things stay positive. Which in application then it's not so simple, because they develop to show that this works in malaria, where one has to make cutoffs first, because otherwise you would run into singularities if you touch zero. And then now the sketch of the proof. First of all, the theorem. If you formulate the assumptions correctly, that means if you have very well defined your norms, then you find out that the functional differential in modeling the dynamics of the structured population has exactly one solution for all time. If the initial values are positive, then the solution stays positive. Because in the beginning you also solve those things for negative initial values. It's clear you don't want to put it in your Banach fixed point theorems, which you use. The analytic steps are clear, what you have to do, but the main problem is to show all the assumptions you need. We assume that the initial boundary values are all given. We reformulate this system as an integral equation, as we would do it for ODE, using this characteristic. And this using the characteristics means you have to change, you have to make transformation in your parameters. That means suddenly you have not function of x, but of transformed. That's a little bit similar to what you sometimes have on other points. And as you know, it's not always clear that things work if you have those things in other points. And you have to control that. And then we show Banach fixed point theorem. There are some approximations necessary. And then we show that the solutions stay positive. And then we have to go back, and we also show that the Lipschitz, that the solutions depend Lipschitz on the data. And then we move in the boundary value equations, have to change again the norms, because it has different structure, and then show there that you also can use a Banach fixed points theorem. And I just see how much time I have. I have another 5 minutes, no? 5 minutes. Okay, I will manage to do that. Because now I list it up again, that you see the main thing, transformation to the functional integral equations. This makes it difficulties, because they goes all in these functional terms are coming in as many transformations as you have. That means if you have n structural variables, you have n different transformations coming in, and say it's not clear that you can get through. Then you solve the functional integration for given boundaries, show that the solution is not non-negative, and and the Lipschitz dependence on the boundary values is the important part. No, initial values are fixed. And then this is important. We know this mapping P1 maps the initial data to at time t and x. But we also need the inverse. We also need the inverse. If you have a u and tx, you have to know where they are coming from. And this is, again, it's people who are doing conservation know that you have to do it, but you have to do it and control it for all parameters, for all equations. And you do that in looking at the inverse structures and show that that if you combine those things, that it's Banach. You can apply for large lambda again Banach fixed point theorem, and then you have the solutions. Now let me just show you this, this transformation you have to control or in the system. That are these transformation to the characteristics. And then you have to study the transformation of the initial values to, this gives a C1 diffeomorphisms. This is the simplest part. And but the other part makes some problems because you have this intersection of the initial plane with the boundaries, but you can show that it's a Lipschitz map. It cannot be a C1 map. And this can be done, and then you end up with this kind of integral equation which you have to solve. And you see in each component you have different integrals depending on the Sij dx that are the parts, how long you have to go to come from tx from the initial values to tx. So, and this gives a contraction. Let me just go on. Wait a moment. Here it is. You have to show it's a contraction. And then, yeah. Here is the part. Then the initial boundary value problem has a unique solution if you have it in L infinity, C0T, L infinity, the data. And if the data are non-negative, then you have a solution. Also, it depends Lipschitz on the initial data. So that's it. Now let me just make some comments. First of all, what are the possible generations? It's clear. We could take also the boundary conditions nonlinear, but it would make it more nasty to read. And you have to have Lipschitz continuity with another norm, therefore we didn't do it. And then spatial spread. There we have a problem. Because doing spatial spread, we have different kind of evolution operators. And this makes some problems. You cannot apply this existence theorem which we have here because this uses characteristics. Also, if you do that, you should think of what are the numerical methods which you would like to use. Numerical methods using this contraction map with a characteristic might not be the best. It could be that Galerkin are better with a special function space. And in fact, if you look there, it has been done by Harman Ray. For chemical reactions, he uses this type of technique. And I think also Peter Teufelhardt, who wrote it for chemicals, most things are done for chemical, from scalar situation for chemicals for growth of one polymer. And then I also would think maybe it's better to give an approach to also an analytic approach in this case by using Galerkin method. Another trick sometimes people do, it goes a little bit in the direction of the perturbation of the by epsilon delta. But delta now in direction of this, in the direction of the structural variables. If you assume that the transition within the structural variables also has some Brownian type term, then you could have that, and then you would, but I think it cannot be assumed in our case, but then you could solve your parabolic problem and then put a limit epsilon tending to 0. I'm finished in 3 minutes. Because this is the last thing what I want. There I can see there is some for simple situation, not for the system. And the main thing is, and that was a reason why I said I have to talk about that, is I think if I did not convince you about that fact, to show this theorem is not so trivial, it can be done, it's not outstanding, but it's really, you have to work. If I have convinced you that we have to look at structured variable situation, then I have achieved what I wanted to do, and the sizes of the structures are in general the dimension is large, because we have a lot of knowledge. It shows you these pictures are just for chemotaxis. You see how many receptors we have there, 5. It's already a lot. 5 dimensions in additional dimension is not. And then we have the following problem. Let's assume this general type of structure. That means we add to the normal diffusion, nonlinear diffusion system, which you have already with chemotaxis, you have that. Add an additional term with transport between the structural structures in the state variable that you get, in general, also nonlinear. We have a linear one, and then on the right-hand side, you have a functional term. You have to get functional terms. And those systems have to be studied, not only for existence, but of reduction. And here, this is an urgent demand. What goes on if you look at nature? Then not all receptors are switched on. In time, you have few, but they change. Writing down the equation, you do not know how they change. Therefore, the mathematics has a challenge. Find methods and algorithms to reduce this huge system according to the dynamics to smaller ones. And this is what I wanted to tell you. And this has to be done. And you also could have something that usually structure variables means you have densities, but they may go to delta distributions. That means some kind of synchronization. If we could show that, then we could write down for the movement of the deltas, we could write down maybe differential equations to do that. But here we have a really open field, and this is what I wanted. Hopefully convince you that it makes sense. What I show you, you might think, why does he go to an art museum? This is a picture of microscopy from Cambridge, just 2013. And it shows growing bacteria, spatially distributed. And what is made visible are polymers. Polymers which are an indicator for the state of this bacteria sitting in a certain point. And what you see there, it's not just an interesting structure. We can talk about that. I have looked a lot of those things. But you also see it in certain regions, you see one color. That means a dominant state, hopefully. Therefore, we may have a chance that these huge systems may reduce to locally to few equations, and then hopefully get this transfer from the information of molecular biology to really biology which can be computed for organs and systems. And thank you very much. Большое спасибо. And the last thing I show you, life has its own hidden forces which can only be discovered by living. That's certain Kierkegaard. But I change it for our situation. Living systems have their own hidden forces which can only be discovered if you are involved with the basic processes. And these are hidden parameters which may get a lot, but we have to reduce them to few. Thank you very much.
Thank you very much for your very colorful talk. Are there questions?
So may I ask a question? I'm not sure if Professor Engel is listening. So I have a question. By chance, I recently spoke to your co-author, N. So by chance, I know a little bit what Diekmann and other people you mentioned do. So roughly speaking, they do the following. To solve the system of nonlinear equations, they prescribe the unknown function at some places, the equation becomes linear, then they solve it by, let's say, semi-group methods, and then they get a solution, and so they have a map of the initially prescribed function and the function they obtained. And then they look for a fixed point. So my question is whether this approach is somehow applicable here or completely
Excuse me.
not.
Yes. First of all, they have no systems. We checked all those things. They have no systems.
Well, they have just a general approach which says
they have,
linearize.
excuse me, if you do that here, you would have to show that this approach works for the systems. It's not clear.
Yeah, so that's my question, whether the approach works.
We checked very carefully, and I had before I went here, Horst Thieme, who is an expert, together he was cooperating, and I asked him, Horst, do you know anything to that? No. And their methods is also, if you refer to papers which they prove, they have something else in mind. They might have been able, I'm sure they are able if they want to show something in this direction, but I don't think this is the same type of method at the moment.
So what is your feeling? So if it is possible to apply, then you can include maybe spatial diffusion? And
no, they don't have spatial. They
don't have, but if this method is applicable,
no, they concentrate on something totally different. They concentrate on evolution of measures, which is something different. Here we are not so much interested in the measure evolution of. We also would like, but they don't have included spatial distributions.
Okay, thanks.
There are papers on a few papers on including spatial effects.
You mentioned in your malaria model that you use Michaelis-Menten kinetics. So this consists of a reversible and irreversible step. Now the question is, how does this apply to your model?
No, excuse me. We do not use kinetics, but we use functions which look like them. Because we have integrals on densities, therefore it's not directly related to the kinetics.
Okay,
we just say we take same kind of functions like in Michaelis-Menten kinetics because you have to limit them. And it's essentially, it says it's limited growth. And you model it by this same type of functions.
Okay. Let me ask the question. For example, about life science. For example, tumors, cancer tumors. It is some collection of cells which demonstrate some unexpected, complicated collective behavior, yes?
Yeah?
Tumors. But there is tumors absolutely liquid on one pole, like ganglioma, the tumors of brains. But there is tumors absolutely solid, very solid, like tumor of soft tissues. There is tumors which are simply holes. And we have to take into account during the modeling all these mechanical space distribution, mechanical properties. It is first part of the question. The second part of the question is about tumors. In practice, in practice applications, we have only 2 tomograph of X-ray photo and 1 diagnostic operation. How we can determine all parameters of process based on the 2? Therefore, it seems that in any individual case should be individual model. There is no general theory for such a process.
Now, wait a moment. The following is the case. Those people who claim that they can treat with mathematical models individual cases are cheating. That's not correct. Because if you want to get the parameters you would need, you would have to kill the people. What you have to do, you have to classify people. You have to put them in certain classes. And it's a task which has to be done. But therefore, what is a reason to have mathematical modeling there? You not go and say, I try to treat you with my mathematical model, but I try to find out if I change under your situation make this changing, for instance, of a bypass or changing a vessel, what might be the effects? And it helps to make decision for the individual person, but no prediction, that's impossible. You cannot, for the reason which you said, you cannot get the parameters which you would need. If you go down to the parameters which you get, you have to simplify your model, which is crazy, you cannot use it anymore. But there it has it's different. It's not for individual therapy, but it helps to the medical doctors to make decisions. And you have to classify, you can say it's that, you can shake, but how do they quantify? How do they make their decisions? They have to know something about the processes, even if you do not know all parameters. If you drive your car, you drive with a motor which was designed with using mathematical model. But if someone would say, please make a mathematical model for your car, I would say it's impossible.
Okay, so I think since it was a long morning, we should close the session by thanking the speaker again, and I suggest that you continue the discussion afterwards.
The pointer.
introduce you chairman of DAAD branch in Moscow, Dr. Gregor Berghorn, and chairman of DFG branch in Moscow, Dr. Jörn Achtenberg. They would like to tell you some information about activity of DFG and DAD in Russia and in Moscow.
Thank you very much for the very kind invitation, and of course we thank very much the organizers that we were given a couple of minutes swiftly to introduce what we are doing. We make it short. We need your attention for only 5 minutes. As you know, there's a Deutsche Forschungsgemeinschaft, there's a DAD, and a lot of other former organizations in Germany dealing with science. And in Moscow and other parts of the world, they have been united in a German center of research and innovation. Here in our city, in Moscow, there is a lot of organizations. It is a DFG, it is a DAD, it is a Helmholtz organization, the German Institute of History, and some others. And they have been united here, as you see, in an organization. The task of it is to introduce German research abroad. So what we are mainly doing, to put it in a nutshell, is we try to introduce the efficiency of German research and science and innovation here in this country. There are about 5 or 6 places in the world where we have these centers, and what we are doing is we introduce the efficiency of Deutsche Forschungsgemeinschaft, the efficiency of German universities. We invite excellent researchers for science talks, for science lectures. We organize conferences or take part in conferences. We organize a special week for German-Russian young scientists. In this year it will take place in St. Petersburg. Our main task is in connection with German economy, working here in Russia, not only in Moscow. We both try to show, to introduce together the efficiency of what German science, German research in connection with economy can do. The organizations you see on these pictures are those who are represented here. It is beside those who are here standing on the tribune, DFG and DAD, the Fraunhofer Society, Max Planck Society, German Historical Institute, Helmholtz, unfortunately they cannot take part today, the Deutsch-Russische Auslandshandelskammer, German-Russian Chamber of Foreign Trade, Rectors Conference, Max Planck, and we all try in a common way to introduce what is Germany like in the field of research. Before I give the microphone to Mr. Achterberg to shortly introduce the DFG, here are our coordinates. We are working not very far away from here on the Leninsky Prospect. I'm the director of the House of Research and Innovation here in Moscow, and Mr. Achterberg is my colleague and deputy, and he will now be informing you on DFG. Thank you.
Yeah, thank you very much, Gregor. Just a few more words on the funding agencies. Among those organizations represented here, not only in Moscow, but also in the circle that is right in the middle of the slide. It's not the first time that we've been here to introduce funding programs and funding possibilities for researchers, but to make it clear among those agencies that are possible for scientific research and scientific projects that can be asked. There is the Humboldt Foundation, there's a DAD and the DFG, and we would always like to make a little presentation in the idea that, first of all, young people get to the DAD if they want to have a grant or a stipend to study a couple of months in Germany. This is why the Academic Exchange Service of Germany is very important. This is mainly for mobility of individual researchers, young researchers. Then when the people come back to Russia or to other countries and stay in science, it's most often the Alexander von Humboldt Foundation where they get to, because this is more specialized, or this agency is more specialized in grants for scientists who are on a senior level. You can ask for a bigger grant, you can ask for a stay of up to a year. And once the people are back in their scientific community, back from Germany, they're looking for projects. You know, after 10 or 15 years in scientific research, you might launch a proposal for a bilateral cooperation with Germany, and then the people come to the DFG. So we have sort of a pyramid from the DAD, the Humboldt Foundation, and the DFG. Everything that I just mentioned now, which is possible and true for the DAD and the Humboldt Foundation, mainly individual grants and other programs, are possible for the DFG as well. This means that if you have partners in Germany, if you'd like to cooperate on a scientific level, if you need money for 3 years that will fund staff, consumables, travel, the DFG is here in Moscow for you available. I left some leaflets on the floor here and outside for further information, and I would like to finish by introducing my colleague here in the Moscow office, Galina Melnikova, who is there responsible as a project coordinator for the collaborationship with German, mainly universities. So please, if we rose your interest, you can make use of this ability, and thank you very much for coming here, because especially during these days we see it is important to keep the bridges in science and culture. Thank you very much, Professor Rühl, that you gave us a couple of minutes from your presentation, because that leads us to you now, because the DAD as a funding agency has been responsible for the financing of your GeoRisk, which you will now surely like to introduce to the audience. Thank you very much.
Dear colleagues, I would like first to tell you that our mathematical school in People's Friendship University of Russia is collaborating with DFG and DAD already more than 15 years, and this cooperation is very, very successful. Our colleagues are very accurate persons, very friendly, and I strongly recommend to all other Russian universities join us. As a result of this cooperation, now we are beginning our international workshop, and chairman of our project GeoRisk, Professor Rühl from Freie Universität in Berlin, will announce you some important things about activity of our project. Please.
Yeah, thank you, Professor Skubashevsky, for this kind introduction. And I will not speak alone here about this project. I also brought my administrative coordinator here, this is Natalia Kolanovska. So we will share the next few minutes to show you what GeoRisk is, and a few of you came already to our desk upstairs in the conference office and you know a bit more, but we would like to show you a few more details. I'm also very grateful that Dr. Berkon is here, who is here the head of the DAD, and we would like to show you what we have done in the first funding period that went from 2009 to 2014 in this German-Russian interdisciplinary science center. And some foreigners who are outside from Germany and Russia have already noticed that GeoRisk is able to also support outstanding mathematicians coming here to Moscow for this conference. So what is GRISC? I already explained the acronym of this project. It is funded by the DAD and the German Foreign Office. It is a multidisciplinary platform for research and education and covers the fields in natural sciences and mathematics, including physics, geophysics, and physical chemistry. And here for this conference, most important, mathematics. We try to bring the leading universities from Germany and Russia together for interdisciplinary research and teaching, and where there is no limitation to the cities that are collaborating, only requirement it must be Germany and Russia, and interdisciplinary work. So what is done? We'd like to solve important scientific questions and problems in experiments and theory. By collaboration, we'd like to educate students, and we would like to find a new dimension on collaboration between Germany and Russia, and the emphasis of GRISC funding goes to young scientists. Of course, the experienced colleagues are not excluded. They're mostly involved in teaching, and our work is mostly on overcoming barriers, cultural barriers, scientific barriers, and also language barriers. Therefore, we only speak English as the official language of GRISC. We involved mostly these disciplines in scientific exchange programs. There is education and teaching. We do conferences as here, workshops, summer schools, and also we developed over the years criteria what is excellence in this field, and we had last year a 3-day evaluation where the entire Center of Excellence was evaluated by German and Russian specialists, and the result of this is that we got asked to renew this project for another 5 years, and it will come at the end to our future perspectives of GRISC. Just that you see that GRISC is organized in a bottom-up approach, so the community in these fields in Russia and Germany is a focus of this project. We need, of course, some help from the coordination offices and the institutions hosting them. This is St. Petersburg State University and Freie Universität Berlin. And we need the funding agency, the DAD, and we have a scientific steering committee that supervises all the scientific quality of all initiatives. Now the details of our project will be now described by Natalia Kolanowska.
Thank you, Professor Rühl. I will tell you about administrative structure of the center. GRISC is divided in 2 coordination units. One is situated at State University of St. Petersburg. The other is at Freie Universität Berlin. The 2 units are in close collaboration between each other. The colleagues in St. Petersburg take care of the participants from German affiliations, so it is useful to contact them regarding the invitations to Russia, visa fees, registration, and other formal questions if you are coming from German institution. The colleagues are also organizing annual workshop called Science and Progress. It is held in Petershof in November each year. Detailed information about this workshop and also oncoming events can be found at our website. You see it here, it is g-risc.org. And here's our unit at Free University Berlin, where Professor Rühl is a scientific coordinator of the project, and I deal with administrative issues. These are, for example, invitations for people from Russia coming to Germany, also assisting by accommodation, help by getting the funds correspondence, solving of all kind of oncoming problems, and much, much more. I would like to show the proceeding in our office, how it looks like. After collecting the submitted proposals, we send them to evaluators. This is Binational Steering Committee, and and then the final statement of the evaluation is done, if the projects are funded or not. Then we send a special form, report on proposals, to all the submitters, which they need to sign and send to us back. After this, all the necessary preparations for the stay can be done. So you see, from the deadline of the call for proposals till the beginning of the research stay, it is approximately, in altogether, 1.5 to 2 months, which is in comparison a very quick operating. I've told you about the proceeding, but what is much more important for you, who can apply for GRISC funds? There are 3 obligatory criteria. First of all, only the researchers based in Russia or Germany can apply. Secondly, the proposals should be interdisciplinary and cover 2 or more fields of natural sciences, mathematics, geophysics, physics, or chemistry. And thirdly, the qualification requirement is bachelor or higher degree. So a bachelor, everybody can apply. And then they have chance to get the funds for young students, PhDs, and postdocs from Russia up to 35 years. They can get supported for research stays up to 2 months. The Germans are also very welcome to apply. Not the Germans as nationality, but people from German affiliations. They can get supported up to 1 month. We also have funds allocated for interdisciplinary summer schools or research workshops like this one. Till now, GRISC has funded 15 workshops in both countries. There is a very good possibility also for experienced teachers, for experienced researchers, to teach a compact interdisciplinary class at the partner institution abroad. And the last but not the least, for excellent students from Russia, there is a possibility to obtain a surplus stipend up to 6 months. The detailed information is on our site. And so how it looks like. This is the GRISC site. You see here on the left different items. If we go to call for proposals and click there, you see all the information listed with deadlines, fund sums, rules, and so on and so on. When is the next call? The next call is issued for October, and you're very welcome to apply. But how to apply for a GRISC proposal? Very important for students, please discuss your project with your supervisor before submitting. He and also the hosting institution should be aware of your plans. That's why we need the letter of acceptance enclosed. This letter indicates that your project can be performed, the required resources are available for you, and you as a visitor can be hosted. How to submit a GRISC proposal? Please don't write such long novels. Only 2 pages are needed. And the official language, as Professor Rul told already, is English. So the submission should be exclusively in English. And important is to submit to our office email. The structure of a GRISC proposal is the following. It should contain title of the project, the names of the heads of involved partner groups, that is important, also the previous work done, the aims of the project, as well as description of the innovative interdisciplinary approach is necessary, and also we need a brief work plan of your activities. The funds that you are requesting should be written, so the sum should be written, the sum which you request. Here's a small brief overview of the statistic of the previous years. As you see, physics, the most projects are related to physics. Mathematics lies somewhere in the middle, so you're very encouraged to improve this and to send us more projects in mathematics. Here's the spread of GRISC activities in both countries. In Germany, as you see, almost each federal land has GRISC cooperator, and in Russia, the western part is strong presented, but we also have cooperating partners in Tomsk and in Vladivostok, for instance. These are some impressions from our participants. These impressions, as well as personal statements, the details of our activities, and also scientific reports can be found in our annual report. We have 2 issues till now. This is the cover of the first one, issued in 2011, and the second one we have here with us. Here the cover of the second annual report. I have here printed copies, plenty of them, so if you're interested, you can come during the break, look through it, and maybe take a copy. And now I give the word back to Professor Rühl.
Okay, thank you. And just one slide to the future. We want to develop this project in the future, so we have envisaged the second funding period till 2019. So we would like to continue with all parts of the project that are successful. We'll try to bring more Germans to Russia. This will be a substantial effort. We are asked by DAD to make this project more sustainable. I'm very grateful that here the DFG is there, so our dream is that we also end up here with this binational programs and DFG funding in the future. We have started an alumni program to keep the community together. We will launch a Young Researchers Award of GRISC in the future. We will improve our public relations so that more people get know about GRISC, and also we are in the middle to improve our administration. You've seen that these are very tight schedules that we're running to get the money to the and the support to the individuals, but we know key is how to improve this even more. Thank you for your attention.
Dear colleagues, now we'll continue our workshop, and Professor Rühl will be our first speaker. The title of his lecture is Uptake and Transport of Nanoparticles and Drugs in Biological Matter. Please.
Okay, thank you so much. First of all, I should explain that I feel very much honored to be invited by Professor Skubaszewski, because I will not show you here differential equations or a few differential equations and functional differential equations. I would like to also to drive your attention towards experimental work, because what is one of the dreams is that experimentalists and the mathematicians and theoreticians work together closely, and that this will in the future be a joint view on the same scientific problems. So I will show you a theme that is not too exotic and that you can also experience from your everyday life. What happens to nanoscopic matter when you bring this to biological matter, So for example, you expose your skin to nanoparticles, and what happens upon drug delivery. So what are the mechanisms how drugs penetrate into the organism? And this is something I would like to show you in greater detail from an experimental point of view. And maybe this brings motivation for those of you who are interested in applied mathematics to develop models and a more general view. First of all, I would like to acknowledge my collaborators who are listed here. There are more collaborators from different institutions who are not listed as co-authors. I'm very grateful to this research that is done, to the German Research Foundation, and mostly here the priority program on bio-nano interaction that has just expired, and the Collaborative Research Center 1112 that is based in Berlin. Now, what can you expect in the next minutes? I will show you how chemists prepare nanoparticles with very unique properties. Then I will show you briefly how they're characterized, and then I will focus mostly on cells and skin, and will show you how these particles and finally drugs are uptaken into skin and cells. This is a scope with a very everyday life perspective for everybody. Nanoscopic objects are nothing exotic. They are produced in bulk quantities, and these bulk quantities, they're used for technological applications. So one thing is, for example, silica. So it's like sand, very small sand spheres that chemists can prepare in a very defined way, in very narrow size distributions, as you would select the size of apples or eggs, by adjusting the chemical conditions, and then you get almost perfect spheres out in bulk quantities. This is the important part. And chemists can do more. They can coat the surface of these particles as they like, so they can choose the material. This is like iron oxide, this is silica outside, and then functionalization, so molecules with distinct properties can be brought to these interfaces. Also, metallic shells can be brought to the outer or inner part of such onion-shaped particles. And this is a beauty that chemists understand within a few nanometers to structure matter, and not only a single particle, but rather many particles. And this is a more complicated particle, as you see here, with different shells, a gold core, a dye, for seeing this in fluorescence microscopy. And they are not only spheres, but also sticks and long-shaped particles can be produced with the length to diameter ratio well adjusted. Or here you see silver in prisms. And silver is used frequently due to the antibacterial action, and this is also a substance that is put into clothing for antibacterial action. The most important part of these particles, that once they're produced, or even you can purchase them, some of them, that the outer functionalization is a crucial property, because this is the part of a particle that interacts with the surroundings. And you see here a whole variety of different molecules of different properties that we have used in the past. And the important part is not only the chemical nature, the important part is the excess charge they carry. You see here, these amines, they can carry a proton, so that if you use this ligand, you have a positively charged particle. And if you use, for example, a pegsilane, this is a negative excess charge. So you can adjust the outermost layer, and you can adjust the charge of the particle. And the charge means the interaction with the surroundings is different depending on the sign of the so-called zeta potential. This is the quantity that specialists express the excess charge of such a particle. I want just to show you very few of these particles and functionalizations with short lengths of ligands and on the surface, with long ones, and with negative charge. These are positively charged and the negatively charged one. This has dramatic consequences. First of all, for aggregation, it is very simple. If your particles have excess charge, they repel each other, everything positively charged, and then there is no aggregation between the particles. And this is here for this kind of ligand that we call AHAPS. I don't want to teach you the details. If you look as a function of time, you see that there is no change in diameter. This is the diameter relative to initial diameter, and you can express this by an exponential function, this change in diameter. In different cell media, this functionalization stays stable, so no aggregation. If you use another ligand, this shorter length ligand, this APS ligand, you see there's a very quick aggregation that is also following an exponential if you evaluate quantitatively the temporal behavior. So this forms big aggregates. So you make out of single, for example, apples, apple pie. You cannot get them apart anymore, and these particles, they stay isolated in cell media. And you can see this with your eyes in electron microscopy. These are the aggregating particles, so these ones, they form really big islands, and these are the non-aggregating ones. They form no islands. So this is important if you want to have an uptake of single particles. One would use this kind of functionalization, and also a positive excess charge is used because the cell membranes have negatively charged patches where the positively charged particles can easily be absorbed. The other important thing is when you stick particles into a cell medium, this functionalization does not stay as you design it as a chemist, but it will be covered by proteins. And we studied the protein adsorption using magnetic particles. This is just a magnetic field where you can hold the particles, and then you can expose them to proteins, for example, to blood plasma, and then you can wash them, and you can do several rinsing steps to look how big is the protein corona on these particles. And this scales with the dilution of the plasma, so you get more proteins absorbed the thicker the plasma is, so it gets just more. And the other question is, of course, what sticks on these particles. So you can distinguish the different proteins, and you see it's mostly the immunoglobulins that stick on the particles as a function of the concentration. And the other important quantity is the temporal exposure. What happens if you expose these particles for short or long time? And the question is there, do the proteins exchange, or do they, when they stick, do they stick and there is no protein exchange? And this temporal behavior, as you see here, is interpreted that there is like a hard protein corona. This means all proteins that stick to the surface never get off. They always stick on such particles. So for these model studies, we get detailed information on the properties of the particles, and now we want to bring them into cells. The cells have a strategy to incorporate everything that is on the membrane by a process that is called endocytosis. And it is a very simple mechanism. When something is on the cell membrane, the cell tries to identify this kind of enemy sitting on the membrane just by incorporating this enemy. And of course, the strategy is well thought of, because if you have the enemy in the cell, you can fight it inside the cell and destroy it. The only problem is if the enemy is, for example, a toxic material, the cell will die and not the enemy. The mechanism works very funny. So there are buckets formed, different mechanisms of buckets, with biochemists can easily distinguish which of the mechanisms that is. But the result is that the particles or whatever is on the surface gets caught in such a bucket, and this bucket gets pulled into the cell, and then it gets processed. This is called endocytosis. And hopefully there are no biochemists who yell at me that I'm oversimplifying. Because this is, if you look in more detail, there's a whole chain of different compartments in the endocytotic pathways that the biochemists, they distinguish between endosomes, early and late endosomes, and lysosomes, and there's even exocytosis where the stuff is ejected out of the cell. So these processes are of interest for biochemists to understand where do the particles go in this chain of processes. And one can follow this in detail. For this, one uses fluorescence microscopy. And you see here the blue, these are the cell nuclei. And these are the neat silica particles. There is very little uptake. So the negatively charged particles get very inefficiently taken up. There are only a few of them in the cells. If you use these aggregating ones, you see the thick patches of aggregated particles that never get taken up. They sit in big flakes on the cell membrane. No take up. Only these single particles, they get efficiently taken up into the cells. So we can adjust by the surface charge the uptake processes into cells. And a more detailed view comes from selective staining, from biochemistry, so that one could see that these particles mostly end up in late endosomes and lysosomes. This is not so important, but that you understand that one knows quite a few details. We get to the skin. The skin is exposed to our environment, and of course there is nanoscopic matter. And the question is, how good is the barrier of our skin regarding nanoscopic matter? We put sunscreen lotion on our skin, and of course people asked, is this dangerous or not? And the answer is very short, no. This is a very perfect protection, but there are weak parts. For example, the hair follicles and the sweat glands. There, particles could invade much deeper into the skin than sticking here on the outermost horny layer that is called by specialists stratum corneum. And this we were interested to study. And our colleagues from dermatology, they are able to prepare these hair follicles, and if you put dye-labeled particles in there, you see really how these dyes and particles go into these hair follicles. And this is, by the way, also used for vaccination. Then there are different kinds of cell and also the uptake into these different cell types. There are Langerhans cells, these are immune cells. These are the yellow marked ones, and there are keratinocytes. These are cells forming the structure of the skin in the viable epidermis. And there are different uptake properties of the of particles into these different cells. So very selective uptake is visible. When the people who have only access to routine methods study the uptake of nanoparticles that are stained into skin, they only see here on a very coarse scale that the particle stay on the surface. They cannot see by optical microscopy single particles. And they came to us and asked, what can we do? We want to know if single particles are somewhere here further underneath. And we suggested them a very selective approach, and this is X-ray microscopy. X-rays, if they're tunable, this is synchrotron radiation. There are about 50 facilities in the world of tunable X-rays using big accelerators, make use of the excitation of the inner bound orbitals or electrons and excite them to unoccupied shell. This is spectroscopy coupled with microscopy that is used for very selective excitation, because each element has different energy structure of their energy levels. And with this, we can distinguish not only different elements, but also different sites in a molecule. And in variable size matter, we also see a size dependency. And this is coupled with a tight focusing of the X-rays from a synchrotron radiation facility by so-called Fresnel zone plates to foci that are of the order of 10 to 20 nanometers. We get a spatial resolution by these scanning transmission X-ray microscopes of 10 to 20 nanometer with full chemical selectivity. And this is a result. You see here the skin. Here are silica particles on the skin surface. This is the outermost stratum corneum, and you see here there are a few single particles that have penetrated a few microns deeper into the skin. Not very deep in, but nevertheless. We can see individual particles. They are roughly 160 nanometer in diameter. We also see how they penetrate into the hair follicles. There they are between the hair shaft and the follicle. So they go deep in. And we see all the details also here in the outermost stratum corneum, but there is never deep penetration. This is a good news. We also looked in individual skin cells, the keratinocyte that I showed before, and we were interested to understand where in a cell do these particles penetrate. And as you see here, this is a micrograph, and you see only a projection. You can never see in 3 dimensions where are the particles, so you could be fooled. And this is something that we try to unravel by tomography experiments, where we tilt the sample. We have to plunge freeze them, so it's a bit of preparation in there, and we have to tune the photon energy accordingly. And this is, as you see here, a keratinocyte full with nanoparticles. And you see here on the left-hand side details of the cell membrane. Here is the nucleus. And the question is, are these particles inside or these particles inside or outside the nucleus? This is difficult to see. And for this, one has to do tomography. And I just show you here in this slide, in this movie, how this sample is tilted. But of course, when we tilt the sample like this, I show you this again, it's very difficult to get to a quantitative view. Of course, you can follow the trajectories. It is much better to use different stacks. So here you see now, we go step by step through the sample. Here you see the membrane of the nucleus coming, and we're looking here into this area where there is uptake in the nucleus, yes or no. This is what is gained from X-ray tomography of single cells. And in one word, these big particles, they're not uptaken into the nucleus, but here we have small, about 60 nanometer big gold particles. They show, for the green ones, they are in the nucleus, the other ones stick on the membrane outside. So we get a very detailed view on such processes. Let me just show you here this movie, and you see here the membrane of the nucleus, and here you see the particles that are inside that can be clearly identified and which is difficult from projection. So you get selective and 3-dimensional information. Our colleagues from veterinarian medicine, they're interested whether for these naked mice, how the particles are uptaken, and can one change the barrier of the skin by different techniques. So there is, for example, inflammatory skin diseases that affect the barrier function, and they looked at different mice. For example, healthy skin, stripped skin, this is just sticky tape, or this crazy glue that people put on the skin and then rip the tape off, and then part of the skin sticks, or they use chemicals to induce a contact dermatitis. And all the attempts showed that the skin barrier stayed intact. The particles never went into the skin. This is good news for us. We're exposed to nanoparticles. There's only one limit. As I show you, this is the a mechanical damage of skin. This is so-called pricked skin. So you go with needles into the skin and you destroy it. Here you see this is a pricking area where the skin is really destroyed. And then we used our well-uptaking particles I showed in the beginning. And there we see that not only near the skin surface, this is here this prick area, mechanical damage, but also much further inside, several tens of microns inside, there were particles uptaken by the Langerhans cells, and you see in detail this is uptake of particles in this endocytotic way. So the only thing that matters is mechanical damage of our skin. Let me, to the end, come to the intentional use of particles for drug delivery. This is subject of our collaborative research area. We're trying to use polymeric structures that can do triggered drug release to treat inflammatory skin diseases such as atopic dermatitis or psoriasis. These are diseases with a very high prevalence in the population, and where the drugs that are used are sometimes difficult to formulate. And if we are able to bring these drugs and polymers, well formulated, into the skin, this would help for therapy a lot, and also for fundamental understanding. This is a cut through our skin. This is a stratum corneum. This area we call the viable epidermis, and here is the dermis. And the question we're asking is, this is so-called topical application of a drug. So this is what you do when you put a cream on your skin. Where do the drugs go after topical application? What can the efficiency of the drug uptake be influenced by nanoscopic structures, drug carriers? And what spatial resolution do we need to study such processes? And what drug concentration can we probe? And optical microscopy, as you see, you might say, well, this is just a distance of 50 to 100 micron that we need to look at. Optical microscopy is sufficient. Yes, for some cases, yes, but I show you what you gain, what insights you gain by this X-ray microscopy technique. We used as a drug dexamethasone. It's a standard drug that is you can buy in all pharmacy stores. And this drug, if you do spectroscopy, this is just exciting the oxygen, this oxygen and this oxygen, and the spectroscopy is very easy so that you can really say which part of the molecule you're exciting. For example, this oxygen you excite when you're here at the left-hand side of this big band. The red one is on the right-hand side. This is the so-called 1s to pi star transition. And we exploit this chemical selectivity by exciting only the drug. And we use this. This is the X-ray absorption spectrum of human skin that is fixed. And we see there is a clear distinction so that we can only excite the drug without exciting the skin. And we get from this a selectivity so that we get two-dimensional maps of drug distribution in our skin. This is optical microscopy, 100 microns deep. Here's the skin surface. This is below the absorption, where no absorption of the drug is. Here is drug absorption. We take the difference, and we see right from a qualitative point of view, most of the drug sticks in the uppermost horny layer of the skin. Now we want to quantify this, We use the so-called Beer-Lambert law. We need the absorption cross-section. This is a molecular property, and we need the thickness of the sample. The thickness of the sample we get from atomic force microscopy in really units of nanometers accuracy. And when we know the cross-section, I will not bug you with, we get to absolute concentration of the drug in the skin. When we integrate here horizontally, and you see here, this is with drug, this is without drug. There is some kind of natural production of these steroids in skin, so that this is the additional drug. And you see also here distribution deeper down after 4 hours of exposure of 0.5% of dexamethasone. You can also refer this to the volume, so these are femtograms per cubic micron. And our colleagues from theoretical physics, they used a diffusion model using the Smoluchowski equation, where the diffusion coefficient is in there. For stationary conditions, they can solve this differential equation, and they can get to time-resolved models how the drug goes into the skin. This is T0, and then down to 22 hours, how the drug flows into the skin. So detailed information. And I'm done in a second. I just show you that you also get detailed views on the skin structure, because there are parts of the skin where there is no uptake at all, and others there is drug uptake. And if we overlay this, you see really that we get details of our skin where there is drug uptake or no uptake. And we cross-check this with atomic force microscopy. These are exactly these pale areas, and these pale areas, these are so-called corneocytes, and these corneocytes are called as a brick, so there is no drug uptake, but only in the so-called mortar. So these are lipids, so the drug flows around these dead cells in the lipophilic phase into the skin. So these details are beautiful to look at, and since our chairman is getting up, I summarize. I've shown you many experimental details, how nanoparticles get into skin, and how we can exploit this for intentional drug delivery. And with this, I thank you for your attention.
Thank you very much for a very interesting lecture.
Could you please make some comment how maybe if you treat the skin with drug, then it may change the permeability for nanoparticles. Have you some experiments on that?
Yes, as I showed you, this oxazolone treatment, this is supposed to change the permeability, but this did not change for the inorganic particles, the uptake behavior. For the drug delivery, this, of course, it is known there are penetration enhancers used in pharmacy also. This is indeed possible to change permeability.
But why do they, for anorganic, why don't they move in? It's a problem of size or what?
It's a size, and there is a rule in pharmacy that if a drug has below a certain molecular weight of about 800 daltons, it's readily taken up. But these are particles that are really in the megadalton range, so if you have several tens of nanometer in diameter, they're much heavier. And that is why they cannot penetrate as easy. But this is what is used in technology.
Thank you once more. And I hope that mathematical models of processes described in this interesting lecture will soon appear in the frames of our G-RISC project.
Yes, and it is my great pleasure. So thank you so much, Professor Skubaszewski. We change now the projection computer because is your presentation, where is this, Professor Skubaszewski? Okay. So I didn't branch this yet. The next contribution, and thank you so much, will be given by our chairman, and he will speak about the non-local elliptic problems and applications to Vlasov-Poisson equations. And Professor Skubaszewski, the floor is yours.
Dear colleagues, first of all, I would like to explain you what does it mean Vlasov equations. Equation 1, this is well-known Poisson equation with respect to unknown function phi, depending on space variable, three-dimensional space variable, and time variable t. This corresponds to well-known Coulomb law. In the right-hand side, we have total density of electric particles. Now, equations 2 are Vlasov equations themselves. Here f beta, this is not exponent, beta corresponds to index. If beta equals to +1, this corresponds to density of positively charged ions, and if beta is equal to -1, this corresponds to electrons. Now, E, this is charge of electron. M beta, this is mass of particle of beta type. Here we have a vector product. B is induction of external magnetic field. C is velocity of light. And in the simplest case, mathematicians considered Vlasov-Poisson equations with respect to space variables in the whole space R3, and with respect to velocities of particles also in the whole space R3. So totally, assuming that we have time, we have 7 variables. In the case of Cauchy problem, one must consider also initial conditions. Here f beta 0 are known initial densities of particles. Therefore, we have 3 unknown functions, f +1, f -1, and phi. This is also unknown potential of electric field. As it is known, in the case of the whole space, one can solve Poisson equation. This is Newtonian potential. And if we substitute 4 into Vlasov equations 2, we obtain the following system of 2 integral differential equations 5. Kernel K, capital, has the following form, and clearly it has weak singularity. Now we obtained new system of equations 5, which is equivalent to system 1, 2. But let us mention that this equation 5 is both non-local and non-linear. Here we have non-local term and non-linear multiplier. Now we can briefly tell you about prehistory in the field of Vlasov equations. Mainly, I'll mention existing theorems. The first group of investigations, I'll mention only a few of them, is connected with a case when kernel K is continuously differentiable. So smoothed kernel. Let me remind you that, in fact, kernel K has weak singularity. So in the case of smoothed kernel, it was proved existence and uniqueness of generalized and classical solutions. In both cases, it was considered existence of global solutions. The case when we have kernel with singularity is much more complicated. Generalized solutions in the case of singular kernel, both for Cauchy problem and for initial boundary value problems, were studied by many authors, beginning from papers of Arseniev. It was under different assumptions. It were proved existence and existence of global generalized solution. Usually the method was the following. Authors considered equations with smoothed kernel, proved existence of solution, and then they passed to weak limit in integral identity. The case of existence of classical solutions was much more complicated. The main results in this field were obtained by well-known German mathematician Jürgen Bad and his former pupils. Roughly speaking, what was done? In the papers of Jürgen Bad, it was proved that if some assumption, which was called later velocity lemma, if some assumption holds, then classical solution exists. And this velocity lemma was proved in a spherically symmetric case. More than this, roughly speaking, in these papers was created the way of investigation of classical solutions. And later, other mathematicians managed, in particular Schäfer and Pfeiffer-Moser, they managed to prove that under general assumptions velocity lemma is true, therefore global classical solution exists. It were published also some other very interesting investigations in this field. Now let us consider the next case, I mean initial boundary value problems. And in this case, it was proved by Weckler and Guo that after reaching the boundary, the trajectories of particles can lose the Hölder properties with respect to initial data. What does it mean? This means that in the general case, we mustn't hope to obtain global classical solution. However, Jan Guo has proved that in some exceptional case, half space with Neumann boundary condition for electric potential phi, they exist global classical solution. This result was published in 1994. And later, more or less recently, under some extra assumptions concerning initial distribution function, Huang and Velasquez has proved the same result for Dirichlet boundary conditions, also in half plane. Something was done also for convex domains. However, in general case, problem of existence of classical solutions for domains with boundary was unsolved, and it was mentioned by many authors. See, for example, papers with reviews of Samarsky and Kozlov. Now, what's the reason why Vlasov equations became so popular? The reason is the following, that these equations are modeling fusion processes in thermonuclear reactors. So in order to make calculations for tokamak, physicists are using, first of all, Vlasov equations. However, unlike majority of mathematical papers, physicists are studying the case of real plasma. And plasma, by definition, this is so-called quasi-neutral media. Plasma contains particles of both sides, negative and positive. This is a great difference. Usually the shape of a thermonuclear reactor has form of torus, like this, and cross-section of this torus in modern situation is not circle or ellipse, no. It has the form of Latin letter, capital letter D. So tokamak has edge. And physicists are trying to keep plasma rope strictly inside camera, because high temperature plasma mustn't reach the walls of the reactor. In this case, reactor will be burned. Temperature in modern reactors is about 200 millionth grade. This is 3 times greater than in the center of our sun. Here you can see another model of reactor, so-called mirror trap. This is long cylinder. And magnetic field has the same direction as axis of cylinder. By the way, in order to provide location of plasma strictly inside a reactor, physicists are using a magnetic field having special shape. In this case, this is the shape of magnetic field. In the case of mirror trap, here in the medium of mirror trap, magnetic field is homogeneous. This is picture of thermonuclear reactor, which was created in Institute of Nuclear Physics in Novosibirsk. Here you can see long cylinder, cylindrical part, and here you can see devices providing a strong external magnetic field. Mathematically speaking, we must find not only classical solutions. We are to find classical solutions having compact supports in the case of bounded domain and supports which are strictly inside our domain at some distance of boundary in the case of unbounded domain. Before, mathematicians didn't consider control of plasma with the help of magnetic field. Usually they didn't consider case of plasma consisting of two particles and of course influence of external magnetic field. Now let us consider the problem in the case of infinite cylinder and formulate the main result of this lecture. This is again Vlasov-Poisson equations, but we consider them not in the whole space R3. We consider them in long cylinder Q. Q is a product of G. This is a bounded domain G with a smooth boundary. Again, we have initial conditions 8, and we must set also boundary conditions for electric potential phi. Let CS0 of Q bar denote the closure of functions from the space CS of Q bar with compact supports. This is in the case of integer S, CS. This is space of S times continuously differentiable functions. In the case of non-integer S, this is Hilbert space. Definition 1, the vector valued function phi f beta, where phi is continuous function on the closed interval 0 t with the values in this Hilbert space, and f beta belongs to the space of continuously differentiable functions on this set, is called classical solution of problem 6-9 if these three functions satisfy equation 6-7, initial conditions 8, and boundary condition 9. It's easy to understand that in this definition the main thing is a choice of functional spaces. Now definition 2. The vector valued function phi 0 f beta 0, where phi 0 belongs to this Hilbert space and f beta 0 belongs to C1 space, is called stationary solution of equations 6-7 with boundary condition 9 if these functions satisfy the equations 10 and stationary Vlasov equations 11 without derivative with respect to t. This is natural. And of course boundary condition 9. We denote by G delta in the plane case set of functions from our domain G which are located at a distance greater than delta from the boundary. And correspondingly Q delta we denote in three-dimensional case set of points from Q which are located at a distance greater than 0 from the cylindrical boundary. We assume that G2 delta is not empty set and denote by delta 0 the largest radius of disk belonging to G2 delta. Assume that the following conditions hold. Condition 1, let initial distribution densities be non-negative functions. This is natural because distribution density functions cannot be negative. And that supports of these functions are lying on some distance to delta from the boundary. This is also natural. Plasma must be located strictly inside our domain. And with respect to velocities v, suppose belong to some ball. We have particles with finite velocities. That's all. Now, condition 2. Let magnetic field be homogeneous with and has the same direction as the axis of our cylinder. And this magnetic field is sufficiently large. One can calculate h is not a very large number, in fact. So in modern physics, it's very easy to create such magnetic fields. You can take corresponding textbook in physics and calculate left part of this inequality. Now, theorem 1. Let B have this form, and then for all delta, rho, delta I mentioned, what does it mean? What does it mean? And rho, such that G to delta and alpha greater than 0, such that G to delta is not empty set, and delta 0 is greater than delta. There exists a stationary solution of equation 6, 7, 0 f 0 beta with boundary condition 9, such that it is infinitely differentiable. Support of f0 beta belongs to, with respect to x, strictly to some interior cylinder. And more than this, the maximum of this stationary solution can be arbitrarily large. Arbitrarily large. If in addition, conditions 1 and 2 hold, then for any t there is an epsilon such that for all initial distributions satisfying conditions 13, there exists a unique classical solution of problem 6, 9. Moreover, the support of distribution, density distributions functions can be, generally speaking, a little bit wider, but still it is located in some interior cylinder, a little bit wider, and in some ball with radius rho. Now let us mention generalizations of this problem. If we would like to consider problems which were studied in the paper of Samarsky, I mean, instead of Poisson equation with Dirichlet problem, we consider Poisson equation with non-local condition 9 prime. Here omega, this is C infinity diffeomorphism, such that this condition holds. So omega maps boundary of G strictly inside G. And here we have also possibly shift with respect to X3. So what does it mean? That these conditions are connecting the values of our unknown electric potential on the boundary, cylindrical boundary, with its values on some other cylinder which is strictly inside our cylinder. And we assume in addition that supremum of B by modular is less than 1. Then it satisfies the following statement, theorem 2. Under assumptions of theorem 1, conclusion of theorem 1 for Vlasov-Poisson equations with non-local conditions also are also fulfilled. Now let me briefly describe the proof of our statement. If we consider the difference between distribution density and stationary solution, we can reduce our system to system 14, 15. However, unlike lots of equations, we have non-homogeneous system of equations 15. For a fixed phi, the equations of characteristics for system 15, this is a system of the first order, has the following form. Denoted by x beta phi, v beta phi, solution of equations 18, 19 with the following initial conditions. And we introduce the following mapping with the help of such functions x and v. Now we denote by x beta phi, v beta phi, the following functions, depending also on auxiliary variable t. X beta phi, so this is a solution of equations 18, 19 with initial conditions 22, 23 at the point tau equals to t. And we said x hat and v hat are equal to x and v at the point tau equals to 0. Now we introduce the following mapping by this formula. Clearly, the mappings S and S hat are inverse mappings. A solution of equations 15 with initial conditions 16 has the following form, 24. This is well-known fact. Now we consider Dirichlet problem 25-26, where g beta phi are given by previous formula 24. And we introduce the operator A by the formula A phi is equal to psi phi. It's easy to understand that it remains to find a unique fixed point of this nonlinear operator. Now set phi equals to 0 in 19. Then we can find in explicit form general solution of system 18, 19. It has the following form. What does it mean? It describes either circles or helices. This is so, physicists well known about such orbits of trajectories of particles in plasma long ago, and they call them Larmor trajectories. Larmor trajectories. So you can see here such helix. And it's easy to understand that if h is sufficiently large, the radius of such helix or circle will be sufficiently small. Therefore, all trajectory in the case of non-perturbed system will remain strictly inside our cylinder. In the case when phi is not equal to 0, the trajectories, but when phi is sufficiently small, the trajectories also belong to cylinder, but they will be slightly changed. The support of distribution functions f beta phi also can be deformed. This is the figure of supports of initial distribution functions, initial distribution functions. And now this is support, it can be deformed also, of distribution function at the moment t, but it still remains at some distance from the boundary. Supports of initial distribution functions with respect to v also can be changed. And finally, they, generally speaking, can have some form, but they preserve in some ball. Now it remains to describe corresponding spaces. This is space of continuous functions phi with the values in this Helder space, having radius less or equal to R1. And if some assumptions from theorem 1 or 2 are fulfilled, we have the following. This operator maps M to sigma into itself, and this is contractive operator. In order to state such properties, one must study first some special Helder estimates of solutions of Vlasov equations for a fixed potential, and study properties of corresponding mappings. It's a little bit difficult thing because you must look attentively that mappings should transform some set into another set of special form. In addition, we must state existence and uniqueness and Helder estimates of solutions for elliptic equations in infinite cylinder. For Dirichlet problem, it's a known fact, but for non-local problem, it's non-trivial. Now I can mention the papers where theorem 1 was stated for half space and for infinite cylinder. Non-local problems were not published yet. And I would like to thank for available advices Professors Kozlov, Filler, Kuksin, Nirenberg, Pyatnitsky, and Vedenyapin, and especially expert in plasma physics, Professor Ilgisonis. That's all. Thank you very much.
Yes. For a moment. So thank you so much, Professor Skubashevsky. We have time for questions. Yes, please.
Да, отвечу по-русски.
Пока что ни одна из известных математических моделей динамики плазменного шнура. И вот пока что ни одна из известных математических моделей динамики плазменного шнура не предложила рекомендаций по подавлению неустойчивости этого плазменного шнура. Ваша модель решает эту задачу?
Если бы она разрешала эту задачу, то, наверное, термоядерный реактор уже давал бы энергию.
Большое спасибо.
Но я хотел сказать следующее, что если вы внимательно посмотрите на модель, описывающую реальную плазму, где частицы разных знаков, то она в принципе не может быть устойчивой, понимаете? Вот, это первое. In English, question was the following, that nobody before couldn't describe correct mathematical model of plasma stabilities and instabilities and how we avoid instabilities. So my answer is the following, that in principle plasma is unstable. But nevertheless, you see there are a lot of different opportunities to achieve corresponding results. Now, sorry, we have no time. I can tell you only briefly that physicists are using not only magnetic field first, also electric field, then different devices, I mean mirror trap and tokamak, are giving different time for life of plasma, and that's all. Thank you. We shall discuss it during coffee break. Thank you.
Yes. I have one question. In one of your last papers, you also used stationary solutions.
Yes.
Did you do this to achieve this goal, or which role do these stationary solutions you constructed just by hand, I think, in this approach?
I didn't mention it, but stationary solutions were constructed in explicit way.
Yeah.
And they can have arbitrary large maximums. So they mustn't be sufficiently small. More than this, it was obtained estimate for existence of time with respect to initial densities. And if you insert real physical coefficients, this more or less corresponds, because this is not model which was calculated from beginning up to the end. This is qualitative theory. Nevertheless, such estimates more or less corresponds to real life of plasma in mirror trap.
Okay, there are more questions. Yes, there is one. Oh, you get a microphone.
I don't understand if your boundary influence your solution, or does your solution depends on the shape of cylinder? Because you don't have particles
yes,
on
in
the
some,
boundary.
wait a moment. In some sense, yes, because we are using for such estimates delta, distance from the boundary, distance from the boundary.
But still, do you have the same solution if you have the same initial day, or okay, let's speak.
No,
all
in the
all
case
data
of stationary
is the same. If I have a bigger cylinder, probably the solution can be the same. No?
Yes, yes, in some situations. But if you are trying to obtain solution with very small radius, you see, like very thin rope, of course we have difference.
Okay.
It is connected in particular with Larmor radius and so on.
Brief question.
In fact, I pick up on the question of Sasha. What in the stationary solution that you consider, in fact, the boundary condition plays a role in the potential.
Yes,
it doesn't
potential.
play a role in the dynamic, because the particle really stay inside because you have a big magnetic field. That's correct?
Yes, because magnetic field is not very big. It's sufficiently large, but you can calculate. It's sufficiently large. I discussed this with physicists, and it was not proved. But nevertheless, the conjecture is the following: that without magnetic field, you cannot obtain stationary solution in cylinder.
Okay, that's. Thank you.
It contains in explicit way all physical parameters, this solution. Induction of magnetic field and so on. It has explicit form.
Okay. I think we had a very vivid discussion. We continue this in coffee break. I also got a question.
Thank you very much.
But we thank first of all Professor Skobaszewski. Thank you so much. And we move on to the last speaker of the session. That's Professor Siegmund from Dresden in Germany. And his topic is a new notion of entropy, which is local in time and space. So.
Mit dem Desktop, dass man den Vortrag wieder hat. Müsste hier sein. Ich glaube,
finden Sie ihn?
Ja, ich habe ihn schon gefunden. Jetzt starten wir noch. Ctrl-L, glaube ich. Ja. Und der Pointer ist auch noch.
Der ist hier oben, die Taste. Ja.
Nee, das
ganz oben ist der Pointer.
Wunderbar. Mikrofon nehme ich von hier. Thank you very much. It's a pleasure for me to be able to give this talk in this beautiful city. It's the first time for me to be here. and I have a good message and a bad message. And the good message is that I'm really have the intention to show you something useful and new. And the bad message is that it's probably not really enough to watch my slides to fully understand it and appreciate it. And I really need to, in the beginning, bring you to a situation where you listen to this question which we are trying to answer. It's a new question which most of you probably have not seen. And also, I'm a pure mathematician. It is really motivated by the applications. And I don't have a blackboard here to draw you some figures, and I refrain from using movies. There's a whiteboard, yes. But yes, it's difficult to see. I already thought about it. But what I do have, I have some 3D space in front of me. So if you watch me now, then I think I can show you the typical application which leads to this theoretical problem. And just imagine for a minute that we have the planet Earth here, like this sphere, which I indicate the surface. And then a typical situation, there are satellites above the Earth. And they take data of the Earth. For example, they measure the currents in the ocean. So this is really happening, and in the internet you can download this data. Every couple of minutes it's updated. You see a snapshot of the vector field of the ocean surface. And that is, of course, a time-varying vector field. So if you write it down in mathematical terms, it would be a time-varying differential equation. And now to get from this application to the theoretic problem, just neglect that it's a curved surface, just think that it's locally just a plane. So now I make a 3D picture very differently. Now I have this 2D plane, which could be the surface of the ocean, but could be anything else here. And I have the other axis here, which is time. And now, since I have this time-varying differential equation, I can just solve it for an arbitrary initial condition starting here. It will be depicting the graph of a solution, just a curve, right? A solution curve. And I can do this for all solution curves, and that's the solution portrait. And this is the situation which I can recover from the data approximately. However, and this is the difference to many classical questions, imagine that here is time, say, 6 hours ago, and now I proceed in time until the present, which is here. And only in this time interval from 6 hours ago until here, I have the data of my time-varying vector field, and this is the data which I want to analyze. And this is very much in contrast to the situation which, since the thesis by Poincaré some 135 years ago, where we sent time to infinity and study the long-term limit when we talk about notions like stability or bifurcation theory and attractors and so on. So now we have only the data, the vector field for these, let's say 6 hours, or maybe even 3 more hours for a prediction. And what are the questions which we're interested in? Well, we want to have maybe barriers of motion, where we have an area in the ocean which pretty much stays together, does not mix so much with another second area. And in classical terms, this would be a separatrix in 2 dimensions, like an invariant manifold, maybe of a hyperbolic equilibrium or whatever. But all these notions do not naturally transfer to the situation which I described. Now, I'm definitely not the first person who is asking that question, but I picked it up from applied people. And for example, people in meteorology, they do this now for decades. What are they doing? They just take an initial value here, right? This is time. They take an initial value, they approximate the solution from the data. That's all very simple. And then they linearize along that solution, and they check maybe taking other initial conditions close to that solution on a circle, and they see in which directions they expand. And then from this time up to the other time, they check the exponential growth rate. And this is, if you send time to infinity, a Lyapunov exponent, of course. They compute the Lyapunov exponents, but only on this bounded time interval. So this is why they call it finite time Lyapunov exponents. And if this is a large Lyapunov exponent corresponding to a direction where the spread is maximum, then this is also this direction in which, if you make a small error in your data or even in the weather forecast prediction or ocean surface prediction, then you get the large error. So this is all very simple, and this is also what they do to get a reliability analysis of their forecasts and so on. Good. Now, how does ergodicity come into play, which is in the title of this talk? Well, ergodicity, like in Shannon's information theory, kind of indicates a maximum rate of loss of information. And by Pezin's formula, this relates in certain situations to a sum of positive Lyapunov exponents. And all these concepts only make sense in the situation when you can send time to infinity, definitely not in this very applied situation where you have only a bounded time interval, and when the vector field is varying with time. So what can you do in this situation? And this is the headline, the task of this project, which I did with a very good student of mine, Lu Huang Duc, PhD student of mine. Then he worked in Vietnam, and now he's back in my group as a postdoc. And so transient metric entropy is the notion which I want to introduce, and it's based on work by Bowen and Thurlin and others. But it contains the new key idea to do exactly that situation when the time interval is compact. And Pezin formula is what I just explained, a classical situation where you can relate it to Lyapunov exponents. And here we have an analog on this compact time domain, which many people call finite time dynamics. This is the keyword which you find in many publications on this situation. And then what is very interesting, how can we recover stable and unstable manifolds from having only data on this compact time interval? And this is called there is no stable and unstable manifold anymore, so people say there are coherent structures which stick together, maybe some rotating vortex over time. And how can we detect them from knowing about entropy? And there we give a new answer to an old problem. It wasn't solved so far. Now, I don't have enough time to give you everything, but I will go slow in the beginning, and then in the end I show you some results. Also some results, but not so many details, just to give you the overview. And if I would be really short, and if you would want to leave the talk in a minute, then I could tell you this is the take-home message. If you accept the notion of differential entropy, which is classical, then I'm able to write down what we did just in terms of that notion, but it doesn't give you the idea, it doesn't tell you what's really going on, but just for reference, you can write down finite time entropy, which is the notion we're talking about in terms of differential entropy, and we are not the first to do this. There is a team about Gary Froiland, Katrin Patbergele, she's at my university now, Gary is in Australia, and they did the following. So T0 is this time where you start, and then you go capital time T steps until you stop. This is the time interval on which you have the information, and then here in this X space you start with an initial condition X0. This is the initial time, the duration, and the starting time. And that, of course, determines one solution curve. And for that solution curve, via its linearization, you talk about something which is called finite time entropy. I'm going into details later. And that can be described via this differential entropy by Boltzmann. And what enters here is a Perron-Frobenius or transfer operator, and there's a smoothing operator involved. So this is what they do, and this notion has some difficulties when you work everything out. And so we suggest something else coming from a very different direction. Still, this is what I do with Lu Huang Duc. We call it finite time metric entropy, and with this differential entropy by Boltzmann, you can still do it, but then you only have to take characteristic functions of balls. Good. So this is the top abstract level, and you don't learn much from that. Now let's go slow and develop the notion. What we want to do as a motivation. So again, I have this 3D picture where we have the time axis here, where we have our two-dimensional X space here, can be arbitrary dimensional just for visualization. And imagine for a second that this is not a time-varying differential equation, but an autonomous linear differential equation. Or maybe just one component is linear, the other component has a higher order term. So this is a phase portrait, so the time axis would just come out of the board, and we have a saddle type of structure with a stable and unstable manifold. And if we can send time to infinity in the autonomous situation, it's so easy to detect this. We have a constant solution, we just linearize its linear algebra. Now, if we only have this interval of time from T0 up to capital T time units later, then we still want to detect this in the special case of an autonomous situation, but we don't know how. And we can do this with our new notion, and the same thing here for this example. We come back to these examples later, showing you how to detect stable and unstable manifolds, and this is the extension, also analogs if the system varies with time, if it exists only for a couple of seconds, the whole system. Okay, just to warm up a little bit, I mean, all this builds, of course, on the classical notion of entropy, and the simplest situation, which you can think of, so that entropy makes sense to talk about. Just imagine that you have a map, capital T, homeomorphism, on, let's say, yes, on a set M, let's even say M is compact, on a compact set M in Rn, And we have a measure, let's assume we take the Lebesgue measure on this compact subset M of Rn, and we assume that this homeomorphism is measure preserving. Good. And now to be able to define the entropy, we have to talk about partitions of M, so just a disjoint union of M. And we have to check what the dynamics, so applying T a couple of times, what that does with that partition. And that's the way how you define entropy. So let's look at the notation for a second. We take such a partition M1 up to ML. And its pre-image under capital T, so T to the minus 1 would be T to the minus 1 M1 up to T to the minus 1 ML. And we can do this with iterates of T inverse. Good. And now if we have two partitions, let's call them alpha and beta, so those collections of sets like here, then we can talk about the refinement of two partitions, which is nothing else than taking intersections between arbitrary elements of the first and the second partition. Sure. Now let's see what happens if we take a finite refinement of partitions. Well, if I know how to refine 2, then by induction I know how to refine k. And which ones am I refining? I'm taking alpha, an original one. I take T to the minus 1 of alpha, I take T to the minus 2 of alpha, I take all those partitions and I refine them so that I get the smallest elements in all these intersections. And it's easy to see that this refinement can be rewritten as those elements in X which have an itinerary, so I check in which of those sets they are, counting the number of iterations. So X is in M some index I0, Tx is in M some index I1 up to Tk minus 1, X is in M some index Ik minus 1. So every X has such an itinerary. Good. And I'm doing this k steps. So these are some preliminaries to be able to define entropy. And now how is it defined? Well, I take, let's read this slide from bottom to top. I take here, with my pointer, I show you the object from the last slide. I take that refinement, k steps of dynamics, and I take a capital H of that. Now what is the capital H of that? Well, I take all elements, let's call them A1 up to AM in that refinement, in that dynamical refinement, and I take their measure, mu of A1 up to mu of AM. And let's just read the next line. Those mu's are called probabilities P1 to Pk and have the minus sum Pi log Pi, the classical formula for the entropy, which in physics you see so often. So you take the probability of those elements, okay, and that gives you the capital H of that refinement. And that is finite time, right? You do it from 0 to k time steps, and then in the next step you let k tend to infinity. Good. And then this is done for an initial partition alpha, and the h, small h mu t alpha is exactly that limit I was just talking about. And you don't do this only for one partition, you do this for all partitions, and then you take the supremum. It's a technical condition, and then you can show that it has nice characterizations with which you can work. So much about classical entropy. And I would not really know how to do this in the situation which I'm interested in. Finite time, non-autonomous, and it's not the most elegant starting point for us. So we found a paper by Bowen from 1971 who characterizes this entropy a little bit differently. And Bowen did that, and Thurlén later, by the way, Bowen did this I think in Oberwolfach, and Thurlén later also did this in Oberwolfach. The alpha is a parameter which I need later, set it to 0, so let you not be confused by alpha, so alpha is 0. What he's doing is he has a local description in space. So look at this expression here, the supremum over Tix minus Tiy, and the weight factor is 1 because alpha is 0. So this is less than epsilon. What is this? Let's go back to the 3D picture. This is a very simple object. So once again, this is the x space. This is the t-axis. I start with an x0 here, and I have one solution on which I'm focusing. Later, I take into account all solutions, but let's just fix this one solution. I go back. So this one solution, and I take an epsilon tube around this solution. This is the epsilon tube around the solution, cylinder type of epsilon tube. And then I'm checking which solutions, starting next to my special one, which starts in x0, which solutions stay in this tube for the whole time interval. This is exactly this object. See, I'm taking all those y starting points of solutions such that compared to my solution starting in x, they stay epsilon close on this whole time interval from 0 to k iterates, right? This is time discrete. This is for motivation time discrete. This is good because this is really a finite time object. I can take this tubular neighborhood, and with this neighborhood, which is called B of x, k time steps epsilon small, what is he doing, Bowen? He's characterizing entropy. This is the left-hand side is entropy if I take the supremum over all partitions. And on the right-hand side, I take the logarithm of the measure of the size, in fact, of that ball. And the 1 over k, this is the exponential rate. And then I take k to infinity and let the size of the ball shrink to 0. Now, having that motivation in mind, this is exactly what we're doing in our situation. Because it's good enough, he shows that his characterization, just what I said in words written down here, his characterization is entropy, so it's a different way to write it down. We can skip that. And now, with that formula, let's say alpha is 0, Lyapunov exponents come into play to say what Pezin's formula is, what I indicated in my introduction. If I have to show this in the figure again so that you see what I'm talking about. X space, t-axis. So I take that piece of the solution, and then I linearize. So I get a linear differential equation, and this is nothing else than describing what is locally happening in the vicinity of that one piece of solution which I'm depicting here. Good. And a linear differential equation, of course, has Lyapunov exponents, as many as the dimension of the system. In our case, it would be 2. Let's call them lambda 1 and lambda 2. And they depend on the initial condition x0 of our special solution. Now, the plus indicates that I only take the positive part of that. So it's negative, the value would be 0. Otherwise, it's the value itself. And I sum up over all those positive Lyapunov exponents, and that is the entropy. That's the best way how you can understand how entropy describes information loss in Shannon's information theory, because it really is some weighted, it's just a sum of those positive Lyapunov exponents which lead finally to small errors being exponentially large in a short time interval, right? This is the rate of information loss. And now let us come to the situation which we are really interested in, where we have this time interval. And I introduce a little bit of notation, which is very handy once you get used to it. Non-autonomous dynamical system is the headline. So a typical situation is the solution of a differential equation on a time interval, just what I showed all the time. X dot equals f of tx. By the way, I mean, I'm very well aware of the fact that this is a workshop where we're talking about functional differential equations. And we did similar things for delay equations, but I decided to introduce the concept instead of showing you the results, which are then even more difficult to motivate. And one can also do this for partial differential equations, in fact, associated to solutions of partial differential equations and related to the models. And this is also one of the projects we're working on. But let's go slow. So let's first explain the concept and then later apply it to various advanced situations. So we're talking now about this Cauchy problem, even finite dimensional, like the situation I described. Phi is denoted by its solution. And yeah, more abstractly viewed, this is a fiber mapping. I want also linearizations along a differential equation, along a special solution, phi, what I just depicted in my 3D picture. I also want this to be a non-autonomous dynamical system. And so the abstract, let's skip this a little bit. The abstract notion would be this. Now this you can focus on. This is just a specialization of a differential geometric fiber bundle structure with a fiber map. What does it say? J is a typical example, it's a subset of the reals. A typical example would be exactly that interval in time. This is the time axis. So from here to there, just this interval. But if I think about the meteorologists who talk about Lyapunov exponents, J would be something else. J would be exactly the starting time, just one point. And then it would be the end time, just the second point. So it would be a 2-point set. And when you talk about finite time Lyapunov exponents, what many people do, then you neglect all the information of the flow in between. So what you really do is very simple. You take the time t map from time now, capital T time units later, or from t0 to t0 plus t. So that would be then your j, just 2 points. And what people do often in algorithms is also that they have intermediate points also where they keep the information of where the solution is. Right? So abstractly speaking, it would be just an interval of, a subset of the reals. Now, for every element in J, we have a subset of Rn. So in our situation, it would be at time t0, it would be just the R2, let's say. And then in the end, or even in between if we want, it would also be the R2. And so we map solutions at an x0 there to time t0 plus t there. So we have this map from here to there, the time t map. And this map would be called phi. And of course, this is to write that it doesn't matter if you start at time s, stop at time u, take that value, and then go to time t. It's the same as going from the first time to the end time without stopping. Co-cycle property, it's often called, which corresponds to the group property of dynamical systems. It's just a formal way to write down that everything is time varying. And then examples are solutions and linearizations along solutions of that structure. Good. And now we do exactly what Bowen did and then Thiele to make this notion of finite time entropy work conceptually. And then we study its properties, which are fortunately very nice. So just still defining the notion, we take an orbit neighborhood of a special solution. So phi t t0x for fixed t0 and fixed x as a function of t has a graph which looks exactly like our solution in this application. And so we take the tubular neighborhood. Well, this is exactly this thing with this distance defined, let alpha be 0. With this distance defined like this, it's just the maximum on this, let's say, compact interval j. And we take this tubular neighborhood. But we fix a time t0. So it could be, just conceptually, you have to really focus on that. We don't take the full tubular neighborhood, but we take slices, right? So at each fixed time t0, let's say we take it at the initial time. Let's call the initial time t0. That's a good way to think about it. So we take all those values which stay then forever epsilon close. Forever means on this subset j. And in our picture, it would be from here to there. So compact. Questions? Okay. And now we follow Bowen and Thiele, and we do nothing else than just generalizing what they did. We take the measure, could be the Lebesgue measure, let's say the Lebesgue measure, of the size of that slice of those starting points which stay epsilon close. But now we have to think about it for a minute to realize that we have to normalize it by the size of the full ball, of the full epsilon ball, which is of course dimension dependent. And also take the length of the interval into account. So this j absolute value means just the maximum of j minus the minimum of j. We are assuming bounded j, so the time interval. Okay, and then you can see that this is really related conceptually to this entropy. And the first result which we get indicates that we did everything right. So what is the statement? Assume a finite time non-autonomous dynamical system on X over a compact J, exactly the situation which I depicted here 3D. And assume that it is linear, for example, arising as the linearization along a solution. Then what you get is that the finite time metric entropy of a linear system does not depend on the starting point. So I take that solution, I linearize around it, so I get a new picture. I get back a little bit, so here's the linear picture, and I take the zero solution of the linearization. Okay, and I could also take the entropy of that linear system, not only for the zero solution, but for any other solution, and it's all the same. Not really surprising, because if you remind yourself that Lyapunov exponents, I mean, they could be defined for arbitrary solutions, but if you do that for a linear system, of course, then they don't depend on the initial condition. And this is the same situation here. And then the good thing which makes everything work is the second statement, that if you want to compute the entropy of phi, phi is here as an exponent, which is this special solution which starts in my x0. If I want to have the entropy of that piece of solution, then what I can do is exactly linearizing along that. So I get the linear system here, and then I compute the entropy of that linearization. It's exactly the same. So this is mathematics at work. I mean, most often we just study global objects by focusing on a local aspect and then linearizing, checking what's happening there, and then gluing everything together, which is the more difficult part, right? Localizing is easy, globalizing is difficult. So this is localizing, right? We look locally at what's happening, and it's really indeed Taylor's formula. You have to carefully check everything, and it's not that short, but it's mainly Taylor's formula to show that. Good, and now we talk about ellipsoids, which shows up here very nicely. And I see that my time is almost over. So this is the latest point for me now to speed things up. So what I'm saying is that assume now the situation that you start here at time t0, you go capital T time units, so you have a time t map. And mainly everything is encoded in how a ball here, which here was R2, so it's a disk. How a disk is deformed by the linear mapping, because now we can talk about linear systems all the time by linearizing, into an ellipsoid, ellipse in 2D. And how the axes are stretched, which is singular values, right? So everything is encoded in the singular values, and we get a representation by ellipsoids intersected. It's difficult to compute the volume in 3D, for example, 4D even more difficult, of 3 ellipsoids, very difficult. Also obvious how to do it, but very difficult with explicit formulas. And now I jump in the last minute. We have a finite time Bayesian formula. You can believe me, but this is the main result. So I show you, this I show you in a figure. Okay, so you remember in the beginning that we had this vector field of, see what I'm drawing? We had a hyperbolic fixed point here, or rest point, and we had this parabola, and we had this line, stable and unstable manifold, very simple situation. And now if you compute the entropy with a weight alpha, which I neglected all the time, which is induced by the vector field, this is a trick, then we get, in the blue axis, we get values of the entropy. The green and the red axis are our x1, x2 space, right, in which this dynamics lives. And then I get high values here, where the stable manifold is, and I get low values where the unstable manifold is. And I computed this only for 2 seconds, let's say, or 2 time units. There's no asymptotics involved here. And we can prove that these so-called ridges, it's like when you go mountain hiking, right? A ridge is when you go up a little bit and left and right it goes down. So differential geometric speaking, you can talk about first and second order derivatives, curvature and gradient. But this is a 0th order ridge where we can talk about maximum and minimum values. And so this is the situation. And these figures are only to show why other methods don't work. And here in this situation, this is a saddle, this is linear. Then we also see this is the maximum and this is the minimum value. And this is the take-home message. So this concept proved already to be useful. Thank you for your attention.
Thank you so much for this very clear presentation. We have time for brief questions, please.
Okay, just a comment coming from fluid mechanics. Okay, at the level of the macroscopic equation, you have a very understood notion of entropy, which is the closest entropy. You move up at the upper level at the Boltzmann equation, going from the Boltzmann to the entropy of Boltzmann to Clausius, something which is very well understood. Now you play the game of deriving the Boltzmann equation from the system of n particle. There is a good proof of Lanford. It's well described in the book of Cerciniani and Illner and Pulverenti. And you see really how the entropy, you can get the entropy at the level of the Boltzmann from the mechanism of the interaction of the art sphere. Now, a thing which was never understood, at least to the best of my knowledge, is to make a connection between the definition of entropy at the level of a dynamical system, and in fact, art sphere is a dynamical system, to the entropy of the Boltzmann equation. And maybe that's what you propose will be a point of view to attack this problem. That's my comment.
Yeah, I'm very happy about your question. You proposed a nice research project. Thank you. Mm-hmm.
Okay, are there more questions or comments to be made? Then I think we thank our speaker again. And we have a very short coffee break that is roughly 5 minutes. And then we reconvene again. And our chair is, what I heard, is our just previous speaker. Oh, he is not chair?
No.
Professor Skubashevsky just told me. Oh. He's the chair.
Yes.
Okay.
И уверен, что вот у него будет уникальное название. Я вынужден переименовывать. Так, сейчас. Вот это вот мы развернем. Что же это такое? Ой, ну я уже давно понял, что надо делать, а ты все думаешь и думаешь. Даже я обращаюсь к компьютеру. Так, теперь смотрите. Вот эта вот кнопочка «Следующий слайд», да? Вот эта вот кнопочка «Предыдущий слайд». Видите? Это следующий, это предыдущий. А вот эта вот кнопочка – это указка, да. Вы будете выступать по-английски, да? Слава тебе, Господи, я хоть чуть-чуть помолчу. Так, значит…
А как там, если несколько слайдов, то есть так это езжать на все?
Ну да, то есть несколько хотите пролистать, несколько раз нажали.
Ну, в принципе, нормально.
Так.
Ладно, спасибо.
Так,
Меня берете?
Дарья Андреевна,
Она
прошу
самая.
вашу флешку.
Пожалуйста. Премиальный джириску в свое время.
Чуть-чуть.
Подарил мне джириску в свое время флешку. У меня она такая. Талисман.
Понятно. Так. Определилась. Проводничок.
Там куча файлов, но он в корне лежит.
В корне, да? Хорошо.
Прям вниз поставьте.
Вот это, да?
Да.
Ну, еще одна умная.
Ну, конечно, умная, вы же меня знаете.
Думаю, все-таки, что далеко не полностью. Подпоручик Дуб говорил, ваше счастье.
Открою?
Сейчас. Так. Оборудование может быть извлечено. Прошу.
Да, спасибо. Да, все работает, наверное.
Так, ну уж как листать вы без меня знаете.
Ну, наверное, разберусь. Только указка, это вот эта верхняя, да?
Совершенно верно.
Окей.
Так, вы будете докладывать по-английски, да? Даша?
The next speaker is Duhan Shakalova, and I will be after her.
I'm not speaking today.
You?
Tomorrow.
You want to speak tomorrow?
Yeah.
Okay.
No, but
listen to you.
I already have that, but I correct some typos, so
Okay.
that's this work.
Just a second. 27.
27, but
Okay.
yeah.
Can you just change the number 3 into the number 4? Let's see. And if I find other blood tomorrow, I will ask you for my talk, but I hope not.
Okay, you are the speaker tomorrow.
Tomorrow, yeah.
27. Okay, I shall just put your lecture to the folder 27.
Because I have already a lecture on that. This one, you...
Which one?
There was a Bardos, which with the DFDA, something.
Talk or talk, which
Yeah.
one? Oh, this one?
Take this one, yeah. This one.
Okay, just a second.
And go into the...
This one? Should I open?
Yeah, let me check if it is the one, if it's the right one. Go to the very first.
Please check.
It's the right date.
I can list
Then
for
go
you
to
in...
245, it's good.
Okay. This one, yes. So I have to return your flashcard.
Yeah.
This one.
Well, that will be the one. Okay, thank you. And if I change this, but if I find some other blunder, I come back once more.
Okay, you're welcome. А где еще один микрофон? А, вот. Okay, let's continue. Please don't be surprised, I am not Professor Zygmunt as it is shown at the program. He just had to leave us soon, so it turns out now it's my duty to be the chairperson. So our first speaker at this session is Lyubov Shagalova from the Institute of Mathematics and Mechanics of Ural branch of the Russian Academy of Sciences, Yekaterinburg. And her talk is called Application of the Method of Characteristics to Construct the Generalized Solutions of the Hamilton-Jacobi Equations with State Constraints.
And first of all, I want to thank the organizers of this conference for the opportunity to participate here and have a talk. So here is the title of my talk, and we will consider the following cache problem which arises in molecular biology, namely in the paper 1, the link on which is in the bottom of the slide. We have the Hamilton-Jacobi equation 1, where the Hamiltonian has the form 2. Here, function f is so-called fitness function. And we can see that Hamiltonian is nonlinear. Also, we have initial condition 3. And this cache problem is the problem with state constraints, because we have constraints on variable x, which is changed from -1 to 1 on this segment, and the variable t is more or equal to 0. So our problem under consideration. And the authors of the mentioned paper, link of which was okay. The link on which was on the previous slide, they was interested in the behavior of a maximum of the solution, and they investigate the behavior of maximum in the case when initial function and the fitness function were quadratic. And the analysis was based on physical interpretations, namely they considered the following function, which they interpreted as potential, and based on behavior of this function, also analyzed behavior of the characteristic system. It is all well known that the classical methods to solve partial differential equation of first order is methods of characteristics. The sense of this method is that the PDE of first order reduced to the system of ordinary differential equations. And for our Hamilton-Jacobi equations, characteristical system has the form 4. There are 3 equations, and the system is considered together with initial conditions 5. But solution can be constructed only locally by these methods. And the next some slides present the behavior of characteristic for various input data. Input data, there are fitness function and initial function. Such picture for fitness and initial function is indicated in the top. And we can see that characteristics intersect, and also we have white regions with there no one characteristics through. There are no one characteristic in this region. And some next slides also presents behavior of characteristics. For example, such behavior or such. We can see here that characteristics are not continuable to the whole time interval. Or such behavior of characteristics. And here we also see that characteristics intersects, and we have non-filled regions where no one characteristic through. So these pictures shows us that we must understand the solution of our Hamilton-Jacobi equation of our Cauchy problem in generalized sense. Also, we have seen that characteristics are not continuable to the whole time interval. And this slide presents the estimates of continuability time. Namely, we suggest that fitness function f is continuously differentiable. So in the segment from -1 to 1, its derivative is bounded. And we can introduce such constant for indexes 1 and 2. And on the next slide, with the help of these constants, there are estimates for continuability time. Theorem 1 presents these estimates, which depends on initial value of variable pair. There are two various cases for estimates. And here, more precise statements of our problem. We understand now that we must understand solution in generalized sense, and some assumptions. Namely, let T star, such T star, low star, will be the minimal from among all continuable times from all characteristics, starting with the initial segment from -1, 1. It is as minimum. And we define, and we have T that is more than 0 and less than T star given. And below we will consider problem, Cauchy problem, Hamilton-Jacobi equation, original problem 1, 3, in the closed bounded region, in the rectangle, which we denoted by such symbol, namely it is a rectangle. And we also will suppose that function, an initial function u0 and the fitness function f are continuously differentiable. This is a more precise statement of our problem. To give the definition of generalized solution, we will need some notions from non-smooth analysis. Namely, at first we will need concepts of SUP and SUP differential. And this slide presents this definition. And also we will need one more set, which is denoted by formula 6. It is defined for continuous function, and it should be mentioned that if function u is Lipschitz continuous, then the set 6 coincides with the famous Clark's subdifferential. And now we are ready to give the definition of generalized solution. Namely, we want to construct a continuous generalized solution. And so the definition, generalized solution of the problem 1, 3 in the region in our rectangle is a continuous function u, which at first satisfies initial condition, this initial condition, and inequalities 7 and 8, respectively for superdifferential and for subdifferential. And also we demand that for points from upper and bottom body of our rectangle, from points from this set, the following inequality is valid. The inequality 9 is valid. we can see that the inequality 9 is the same as the inequality 8. But 8 is must be fulfilled for the whole subdifferential, and 9 we demand only for those elements from subdifferential that also belongs to Clark subdifferential. This is our formal definition of generalized solution. And now some words to discuss this this definition. In the theory of partial differential equation of first order, there are many concepts of generalized solution. Among them, two concepts are very popular. At first, the concept of viscosity solution, which was introduced by Crandall and Lyons. Here is the link to the first pioneer work paper. And the concept of minimax solution that was independently introduced by Andrei Subbotin. And if we consider Hamilton-Jacobi equation in open region, then under very general assumptions, concepts of minimax and viscosity solutions are equivalent. This equivalence was shown by Andrei Subbotin. And also these concepts of viscosity solution and minimax solution can be considered as generalization of a classical methods of characteristics. And to this question, this book by Nina Subbotina is devoted. Why there are so wonderful concepts of generalized solution, and why we introduced our own definition of generalized solution. As concerns minimax solution, they were not considered on bounded regions, only in open regions. Viscosity solution were considered, but we are not satisfied with this concept also. Why? It is one property of subdifferential in the body points. Let us assume that in body points T star, X star, it is body point, subdifferential is non-empty. And let N is outward directed normal to this our region. Then, if vector L belongs to subdifferential, if subdifferential is non-empty, then, as it is not difficult to notice from the definition of subdifferential, it is follows that for any number k, positive number k, the following inclusion is valid. With vector L, any vector of such a form also belongs to subdifferential. And if in our problem in body points subdifferential is non-empty, body points upper body on upper body or lower body, the outward normal respectively is vector 0, 1, and here vector 0, -1. And we can see that the inequality for subdifferential is violated in body points. For example, if for definiteness we take the point when x equal 1, then for fulfillment of inequality 8, it is necessary the next condition. And we can say that for any positive k, it is not satisfied. This inequality is obviously violated. So there are not viscosity solution in our problem which has non-empty subdifferential in body points. And as concern known theorems of existence for viscosity solution, one of the essential assumptions is assumptions on coexistentiveness of the Hamiltonian, namely this condition, condition 11. And this condition is not valid in our case. For example, is violated when x is equal 1 or x is equal minus 1. It is not difficult to notice. So we cannot use the famous theorems on existence for viscosity solution. And so we introduced our own concepts of generalized solution. We introduced such solution, and so the questions arises: does such a solution exist? And if it exists, does it is unique or not? And we have answer to these questions, namely in the paper indicated here and below of the slides. Our paper with Nina Subotina. By methods of optimal control theory, we have shown that continuous generalized, in the sense of our definition 1, solution exists, but it is not unique. And all such solutions are subdifferential functions. Namely, the subdifferential is non-empty for every interior point of our rectangle. Such interesting property of the solution. And the theorem on this slide presents the structure of the solution. It is formed from the characteristic, but characteristics start not only from initial manifold where t is equal 0. We continue initial function u0 to the body of to the upper and low body of our rectangle by continuously differentiable function phi. And then we introduced, we have characteristics starting from initial manifold and from the body, and in the point t x, we considered all such characteristics and consider the value of such expression. And the maximum of this expression will be the value of our generalized solution. So the generalized solution is constructed from characteristics. And it is not unique, it is not difficult to understand why is such situation, because we can use different function phi to continue our initial value, to reduce Cauchy problem to Dirichlet problem. So there is the generalized solution exists and is not unique. And in the next slide, in the following slide, there are some pictures of the graph of generalized solution for various initial data fitness and initial function. And here, by blue color, denotes characteristics starting from the initial manifold, from the segment where t is equal 0. It is starting from the initial manifold characteristic. And in green color, characteristics starting from the body of our rectangle, from low body and upper body. And this example is good example because the characteristics starting from initial manifold and from the upper and low body are not intersects. And we have another example in the next slide for such initial data. And here we can see that generalized solutions are formed only from the characteristics that start from upper body of our rectangle. And the original characteristic, which starts from the initial manifold where t is equal 0, don't participate in our solution. And it is not a very good situation. So the problem arises. And here in the slides, the first paragraph is the repeating of what I have said, and the problem. We must define the extension of initial function U0 in such a way that in the region where characteristics starting from the initial set exists, the generalized solution would be formed only from this characteristic without participating characteristics starting from the body. And this problem we solve only in special case, namely for this case, new assumption, under this assumption A1, A3. These assumptions to initial function U0 and fitness function. Here, if we from the assumption A3, it follows that our rectangle is divided into 3 parts. First part is the region G0, which is bounded by characteristics starting from the corner -1, where x is equal -1, and the characteristics starting from the corner of our rectangle where x is equal 1. It is the region G0, and we have 2 another regions. One is below this region, G-, and another region is above, G+. And we, in the next slide, presented some properties of solution of characteristic systems considered under new assumption A1, A3. And using these properties, which presented by lemma 1, lemma 2, lemma 3, and lemma 4, using these properties, we can construct generalized solution with desired property. Namely, in region G0, solution is subdifferential and it can be presented by such representative formula. We can see that it is constructed from characteristics starting from initial manifold where t is equal 0, and in the point tx we choose those characteristics where the value of the expression is maximum. In region G-, solution is differentiable. Function is formed from characteristics starting from low corner. Here we change the parameter P0 and we received the family of such characteristics. And in region G+, the situation is analogous with the previous situation. The solution also is differentiable and it is formed from characteristics starting from the upper corner of rectangle, and here we change the parameter P0 from minus infinity. And in the body, using lemmas 3 and 4, we defined the value of our solution by such a way, and the low boundary, and by such a way in the upper boundary where x is equal to is equal 1. And so by such constructing, we receive a continuous solution with desirable. I have no time. And I also show some simulation results and finished. And here, for such initial, for such input data, it is the projection on TX plane, and it is space picture, and also for another initial data, projection and space picture. Here is references, and here, thank you for your attention.
Let's send the speaker. Any questions or comments? Yes, please. Professor Panov.
As is known, Hamiltonian-Cobb equations can be reduced to conservation law, to first-order quasi-linear equation. And viscosity solution correspond to entropy solution in Khrushchev sense. And boundary value problem for such equation is well developed. There is theory of initial boundary value problem with existence and uniqueness. In this sense, more natural Neyman problem, because reduction is, if you consider your equation U, solution U, when derivative Ux is a solution of conservation law.
It may be, but only in the interior of our rectangle. And we have difficulties with the border.
Yes, yes, but boundary value problem is well defined for conservation laws.
Defined?
Yes.
And
there is a
thank you, I will see.
Bardoli Rondelec, for instance.
And you recommend to see Khrushchev's papers?
Yes, yes.
Okay,
Khrushchev paper, this is a Cauchy problem, of course, but there is a generalization. It was some papers, for instance, Bardoli Rondelec, from boundary value problem for multidimensional conservation law.
No,
my question is, why did you use this approach, reduction of your Hamiltonian-Cobb equation to conservation law? So I recommend to use this approach.
I is more familiar with Minimax solution, and when we want to use such concepts, we have difficulties because such solutions were considered only for open regions. Then we began to see viscosity solution. There are also problems with subdifferentials on border if subdifferential is non-empty, and all known theorems for viscosity solution demands the constituency of Hamiltonian, which is not valid in our case. And so we invent our own definition. And I don't work with conversation laws, and we will see. And thank you for the question.
Thank you.
Any more questions or comments? Okay, then let's thank our speaker again. Я перед тобой отчитаюсь. Regarding comments about time of several very attentive participants, I have to say that our last talk is cancelled, so I decided to provide other speakers slightly longer time for their talks. So since we have no last talk, we have only one speaker for tomorrow. Excuse me, for today or for tonight. So our last but not least speaker is Daria Neverova from our host, People's Friendship University. And she will talk about the regularity of solutions to the second and third boundary value problem for differential difference equations. Please.
Yes, thank you very much. I hope that today I won't be the last speaker because today is a banquet. I hope that everybody remember about this. So, yes, my talk devoted to the relation between classical and generalized solution of boundary value problem for differential difference equation. And firstly, I want to speak about the background of this problem. Usually the feedback and the control system leads us to the delay at the control system. And here you can see the scheme of the control system, and y of t, this is the state of the system, and u of t, this is the control of the system. And if we have the delay in the senior term of this system, then we can describe this system using this equation. Of course, we need to know the history, the prehistory of the system. That's why this initial condition is set. Turns out that such a control problem has closely connection with variational problems. And the solutions of, it turns out that the function y that guarantee us the minimum of these variational problems should satisfy such equation. That is the differential difference equation, and it has boundary value problems. That's why the solutions, that's why our attention to such kind of problems is very important. Another application is the application to the elastic deformation of complicated materials, sandwich materials that usually used in the modern aircraft technology. They use sandwich panels with different plates and shells, what you can see here. In the work of Professor Ananov and Professor Skubachevsky, this problem was considered at 76, sorry. Also, non-local problems arise in the plasma theory problems, and they have strongly connections with boundary value problems for differential difference equation. We can see it here. Here you can see the differential equations with non-local, a boundary value problem for differential difference equation. Here, operator R is the difference operator, and this problem is almost is equivalent to the problem that you can see below. That is just differential equations, but with non-locally boundary conditions. Here, this is the connection between these two problems. And you can see, it is the well-known fact that the solution of boundary value problems for differential difference equation is not smooth. This green line, this is the solution of this boundary value problem. And the red line, this is the solution of this equation. So, since the smoothness can be violated for such problems, the investigation of the conditions when a solution of boundary value problems are smooth, it's very interesting. And earlier, Professor Skubachevsky has some results about generalized solution, but he has no result about classical solutions. And my talk devoted to this problem. Firstly, before I will speak about setting, I want to explain you how our difference operator behave. So you can see here some function u, and when we apply our difference separator to this function, assume that all coefficients here, b minus 1, b0, and b1 equals 1, then this function will move to the right, will move to the left, and after that, the result of acting of this operator will be the sum of all these functions that you can see at the blue line. So, now about the problem. We consider the following differential difference equations that at the finite interval, finite. This equation number 1. Here, operators Ri is the difference operators that are described as I told at the previous slide. For this differential difference equation, we set boundary conditions. Conditions 2, we need to set condition 2 because the shifts of the difference operator map the points from the domain out of domain. And since my talk is called about the smoothness of solution of the second or third boundary value problem, we need to set Neumann or Robin boundary conditions that you can see here. Of course, if sigma 1 or sigma 2 equals 0, we have the second boundary problem. If they are not 0, this is the third boundary value problem. Now let me introduce the definition of generalized solution of this problem. And a function u from the domain of unbounded operator AR that you can see here is called generalized solution of the problem 1, 3 if this relation is fulfilled. About the solvability result for this problem in the terms of generalized solution. It was proved in our joint work with Professor Skubachevsky that there exists a unique generalized solution of such problem, and there was a result that shows that generalized solution are smooth on the subintervals. Let me explain it using the example. Now the length of our interval equals 2, and in this case, and shifts equals 1, and in this case, for this interval, we have two subintervals, Q11 and Q12. So, if some non-degenerative conditions are fulfilled, and function f of our right-hand side of our equation is continuous, then generalized solution of boundary value problem will belong to C2 space of this interval, Q11 and Q12. But the point is what will happen between this interval and the point 1. How our function will behave here. Yes, yes, Alexander Ilyich. Yes, here n equals 1 and d equals 2, okay? I just show this an example, as an example, okay? Yeah. So now let me determine the classical solution because we try to find the connection between classical and generalized. So again, let right-hand side of our equation is continuous function, and a function u from the space C2 is called classical solution of our problem if this relation is fulfilled and our function, of course, satisfied our equation and boundary conditions for all x from our interval. Of course, it is obvious that if function f is classical solution, that is a generalized solution, like in the classical theory. And now I want to present the main result for third and second boundary value problem. That is, again, I try to explain the simplest case when d equals 2. Of course, this is result general and for arbitrary length of the interval, but here it's easy to present, it's easy to understand, I hope. Again, let's some non-degenerative conditions for coefficients fulfilled, and f is the continuous function. Then let u is a generalized solution to our problem, and these coefficients equals 0 at the point 1. Then u of x is the classical solution to this problem. Let me note that if coefficients of our difference operator are constant, then it means that generalized solution will be classical only when we don't have any shifts at operator R0 and R1. So the generalized solution will be classical only if we have shifts at that term that has no derivatives. And the necessary conditions, if one of these conditions is not satisfied, then there exists a right-hand side that is continuous, such that we can find the generalized solution u of x to the boundary value problem 1, 3 that is not classical. Again, here it's easy to notice that we have the distance between these two theorems. Because at the first theorem we have these coefficients, this condition, and at the second part we don't have such one. For example, for Dirichlet boundary value problem, we have the criteria. Sufficient conditions and necessary are coincide. For Dirichlet and Robin boundary value problem, they are different. This is not very new result. For me, it was a result of last year, because now I'm working on the multidimensional case, and such technique for multidimensional case works. And I hope for new results maybe in the month. So that's all. Thank you for your attention.
Please, questions, comments? Yes, please.
Yes, of course.
In your equation,
yes.
You write R0u and then the second derivative.
Yes. Yes.
And in the second term, you write another order, first derivative, and then the coefficient, the operator.
Yes.
Is it all right?
It's all right, but I know how to work if we have a, how to say, divergent form or non-divergent form.
Your coefficients B
it depends. Of course, I suppose.
Continuous.
Yes, I suppose that they are continuous, of course.
Okay.
Okay.
Any more questions? Okay, let me ask a question. The necessary condition contains the formulation, then there exists a right-hand side f from. So probably it is possible to select a subset of the space C of 0D such that we can find the generalized solution for any f from that subset. Have you made any steps in that direction?
Professor Muravnik, thank you for this question, but I have not goes to this direction, but maybe I need to check, but I think that it's not possible to found such kind of function from C0 that will be C0 of the set from 0 to D. Maybe it should be some subsets, then it will works. And but in the end, we consider the whole interval, it's not possible, because I always can't find the counter example for this case.
I see, but anyway, well, you mean that this subset must be independent of the condition. I mean, for each condition, any condition
They are
selects
independent,
its own subset.
Yes, yes.
So the question is how to characterize this subset having the particular condition. Okay, I understand that it is immediately
now the
to
paper,
answer.
now the paper is almost published in the Israeli journal, Functional Differential Equations, and there are the proof. And we I have special for every condition. I have a counterexample. Let's say this.
Well, I asked actually something else, but well,
maybe I didn't
not
understand.
now.
Yeah,
Okay.
yeah, sorry.
Yes, let's thank our speaker. If there are no more questions or comments, no. Okay, let us thank our speaker again. And this is the end of our conference day for today. Probably our speaker would like to make any announcement, already being not a speaker but an organizer.
So maybe at 7 o'clock, the people who has registered for banquet, please come to the main building where was the reception party, at the same place. Yes, thank you.
Probably this is really end for today.
Я понимаю, нет, но это очевидно довольно, что оно должно писаться. Вот, значит, вот я хочу сказать уже по существу.
Да.
Значит, нет, это было хреновенно. Значит, смотрите, вам правильно сделали замечание. И может быть даже,
еще раз
если написать производную после, первую производную после, то вам будет, то может быть вы и сможете критерий сделать. Вот. Потому что, нет, может быть и нет, но тот факт, что два главных члена пишутся в противоположных направлениях, это не очень естественно.
Я поняла, ну можно, да.
На самом деле у меня был другой вопрос. А почему вообще так странно пишется? Значит, можно писать сначала производное, потом, ну ладно. Можно писать одну, ну как обычно пишут, чаще всего пишут, одну производную, потом матрицу, потом вторую.
Да.
Вот. Вы пишете вторую производную потом, да? Ну, дальше это, наверное, вопрос не к вам, а к шефу, но тем не менее. Что такое классическое решение? Классическое решение – это то, когда все производные, которые написаны, существуют.
Да.
Так зачем ему быть C2-то? C2 должно быть то, что после матрицы получится.
Да.
Вот. Значит,
Там так и получается в определении.
Нет, в определении вы требуете, чтобы оно было C2, как бы это сказать, пинком еще дополнительно.